let me know when you can see it, right?
Wilco.
Okay. Meanwhile, I'll get some more paper.
Can you see it, James? Oh, there we go.
Yeah, we're live.
Okay, so thank you again for joining. So everything okay with the stream? Yeah.
Yeah. We're live. We're rolling.
Okay, good. So continuing on, I've got my good friends James Gill and Dan Reeve. So I never actually introduced you, Dan. So Dan and I met in first year of university, and we continue to be friends. Sorry, that was a terrible one.
Yeah, what a great introduction that is. Yeah. Thank you.
Oh God, I'm so sorry. My fullest apologies. So
No. You've got your head in numbers, not in stories.
Quite an achievement, Dan. Quite an achievement.
Yes, we were friends at one time, and we have remained friends.
So I don't know how much you want to reveal about yourself, Dan. That's why I stalled on that. So do you want to say anything about yourself while I think about this question here?
Born in 1990. I can go all the way back if I like.
Well,
Dan, long number on the front of my credit card is this.
Yeah, that's not really what I meant. I meant in terms. I mentioned that James was a statistician.
Yeah. So yeah, we lived together for a year as well in fourth year.
I think we lived together for the last 2 years. Oh, was it only fourth year that we lived together?
Only fourth year. James lived with you in the third year of uni.
Yeah, that's right. And then and actually Dan has a special place among my friends. He is the person I think we did the most courses, the same courses together of anybody else. So
that would be about right. I don't know. Maybe Mike Bushell. He might have done some. No, he might have crossed over a little bit.
So in fourth year, we did all the same courses, didn't we? And
pretty much.
There weren't that many of the courses. Like, say, I think you did like Lebesgue integration and measure theory. James started to diverge from us when it became. So when you do a degree in most universities, but particularly in ours, after the first year and a half of compulsory modules, you can choose the modules that you do after that. So it's a lot of optional content, and we very much went down the pure route, and James went down the statistics route, which just makes me want to vomit. So I didn't do any of that. We stayed for the 4 years, did a lot of abstract algebra, topology, that sort of thing, and it was a great time,
Yeah, I have to admit, I think that I chose the algebra modules mostly because I was fairly lazy. Like, I always felt like if I went down a stats route that I would have to work a lot harder.
Yeah, so you're kind of choosing what you're naturally strong at.
Yeah, I was just choosing the easiest stuff, and I found that to be the easiest thing.
Yeah, which is fine, but it's also the most interesting. I would say. I'm getting a little bit of audio back. Are either of you using speakers?
I just put myself on mute. Did that make it any better?
I don't know because it stopped. I'll let you know if it happens again. So anyway, let's get on to, speaking of abstract algebra, we've got some group theory here. So we've talked about sets. So these are just collections of things. And a binary operation, it's got nothing to do with binary. It's called binary because it has two inputs. So a binary operation is just you take two inputs and you get an output. So for example, addition, multiplication, subtraction, division, these are all binary operations as long as you're in the right set and it's all closed and everything like that. Let's not worry too much about that. But for the purposes of this explanation, that's what a binary operation is. But when you get to a certain stage, you want to move away from specific operations and specific sets. So we start to talk in general about operations. So rather than talking specifically about addition or multiplication, you talk abstractly and just in terms of general binary operations. So it's an associative operation. And now in fact, let's just get this out of the way now. I am going to write AB is equal to A star B because, you know, who's got time for that? Certainly not me. I've only got 16 hours to go. The fact that star is associative, this means that for all A, B, C in G, A, B, C is equal to A, B, C. And this is like what I think of as the unsung hero among the axioms, because this is one of the most powerful things that we use on a day-to-day basis, but we never really think about the fact that it actually works. And it just means that, addition and multiplication are associative operations. It means that you can basically add them up in any order. So if you've ever thought about 3 plus 4 plus 7, the natural way to do this for a mathematician would be to add up those first. So we're using commutativity and associativity there, but it means that you can do 3 plus 4 is 7 and then add 7 to do 14, or you can do 4 plus 7 is 11, add 3, and you get the same answer. Not every operation is associative. So for example, exponentiation, if you've got 3 to the power of 2 to the power of 4, if you do it like this, that's 3 to the power of 16, which is a whopping great number. But if you do it like this, then you get 9 to the power of 4, which is a more manageable number. You know, it's only, you know, it's whatever it is, you know, but it's a lot smaller than that is, you know, because that is actually 9 to the power of 8, really, isn't it? So not every operation is associative. But anyway, that's what associative means.
My favorite, just to cut in here, my favorite non-commutative operation, this is one that actually Nige Ray told us about, was putting your socks on before your shoes gives a very different outcome as if you put your shoes on and then your socks.
Yeah, that's commutativity though, isn't it? I think associativity, colloquial.
Yeah, associativity, yes. Of course.
Yeah.
You're right.
Or the umbrella, you know, if you put your umbrella up and then go for a walk in the rain, it's a different outcome as if you go for a walk in the rain and then put your umbrella up.
Yes.
So E is an identity if EG equals G for all G in G. So, you know, the additive identity is 0 because A plus 0 equals A for any A. And the multiplicative identity is 1. Which is 1 is usually the notation we use in group theory rather than this E. So 1 times x is equal to x for all x. You know, timesing by 1 changes nothing. So that's what it means by an identity. And commutativity means that we can swap around the things that we're doing the operation on and get the same answer. And again, that is something that we take for granted in a lot of our operations, but it isn't always true. The most simple mathematical example is subtraction. 3 subtract 5 is not the same as 5 subtract 3. I don't like that example for a specific reason I won't go into right now. But you know, we consider commutativity to be like quite obvious, but it isn't always. And in fact, in most cases in the study of groups, groups are generally not commutative. So you've got to be careful when you're working with groups. And in fact, we did 2 courses, didn't we, Dan, at university? We did a course on commutative algebra, and we did an entire course on non-commutative algebra. The second of which was a lot harder, in my opinion. I thought it was a lot harder. It's all that ring theory, isn't it? And like non-commutative rings, it's just really, really hard. Okay, so G endowed with this operation is a group if star is associative. There exists E in G such that EG equals G for all G in G. So it's just saying that an identity exists. And for all G in G, there exists H in G with GH equal to HG equal to, let's use E because it wants us to use E for some reason instead of 1. So inverses exist. So groups are these kind of really nice symmetric structures where, you know, you've got a bunch of elements, you can times them together to get other elements in the group. The times, what I'm calling times, might not necessarily be times, it's just some general operation. The times functions nicely, it's associative. There's an identity element, there's like a 1 element, and every element has a partner that you can times it by to get to 1. So that's what a group is. Okay, prove that the identity is a unique element in a group. So we've said that there is an identity element, and in fact, once you've set up this group structure, you are forced into a situation where you only ever have one identity. It's always unique, and proofs of uniqueness always go the same way. Assume E and let's say F are identities. Then that means that EG equals G for all G in G, and it means that it means that FG equals G for all G in G. And there's usually two nice ways of going about this. So if you take a specific G in G, then EG is equal to G, but we also know that FG is equal to G. Since we know that every element has an inverse, which we usually denote by that, so we know that G times G inverse equals, well, an identity in this case, then that means if EG is equal to FG, then that means EG G inverse is equal to FG G inverse, and that's equal to E, which is E, and that's equal to FE, which is F. So E is the same as F. The cleaner, nicer way is just to consider what EF is. So on the one hand, it must be equal to E, because F times anything is itself, but on the other hand, it must be equal to F, because E times anything equals that thing. So we get that F is equal to E. So you only ever have one identity element in a group. Show that the inverse of each element is unique. So guess what we're going to do here? Assume A and B are inverses of G. In other words, AG is equal to the identity and BG is equal to the identity. So what's the kind of nicest way of going about this? Let's just do that same game from before. AG is equal to BG, and that means that A times G times A, because of associativity, is equal to that, and that means that, and that means that. So A is equal to B. So proofs of uniqueness, they always go the same way in maths. You assume you've got more than one of them, and then eventually deduce that they must be the same. Okay, and we're going to prove now that for all xy in G, that xy inverse is equal to y inverse x inverse. Well, the inverse of xy is that if when we times by that, we get the identity. And by associativity, we're allowed to just times these together in whatever way we want, as long as we don't switch them round, because we're not assuming it's commutative. So that's x inverse. The identity does nothing, so this is equal to the identity. So it is indeed the case that the inverse of xy is y inverse x inverse. Okay, time for some more modular arithmetic, I think, is what we're going to be doing next. So let S be the set of, okay, so these are congruence classes. So what this means, 321 is actually the set containing 3, 24, 45, and so on that way, and deducting 21 as well, so minus 18 and so on that way. So it's actually the set of all integers that are congruent to 3 modulo 21. So, but these sorts of things can sometimes function like groups if they meet certain certain criteria. I should add, actually, I didn't include that closure is part of the definition of a group. The reason I didn't do that is because usually we put the definition of a binary operation on G is a function from G cross G to G. So by definition, it is closed. So anyone with some group theory knowledge wondering about that, that's why I didn't include that as part of the definition of a group. So by trial and error, find an inverse of, find the identity elements. So, okay, by trial and error. So let's do 3 times 6, that's 18. 3 times 9 is 27, which is congruent to 6. 3 times 12 is 36, which is congruent to 15. 3 times 15 is 45, which is congruent to 3. There we go. So x 21 we'll do is 15, 21. So 15 is functioning as the identity of this group. Okay, show that that is an identity element. Oh, right, okay, so we're going to actually just go ahead and show. So 3, 6, 9, 12, 15, 18, times them all by 15, and what we should get is the same as what we started. So we're going to get a number, and then we're going to reduce it modulo 21, and what we should get is all of these numbers appearing again here. So 3 times 15 is 45, which we've already said is congruent to 3 mod. I'll just do mod 21 on that bit at the end. 6 times 15, that is 90. So 90, if we do, the quickest way is probably just to do that, subtract 21, keep subtracting 21 until we get to 6. So that's good. 9 times, I suppose I could just add 45 onto each of these. That'll be a little bit quicker, won't it? 180, 225, 270. So 135. Just keep subtracting 21. That's 9. And in fact, we've got from there to there by adding 45. And 45 modulo 21 is 3. So in fact, we are literally just adding 3 each time here. So I think that's proof enough for this question before I bore everybody, including myself, to tears. Write down 2 multiplication tables. So sometimes we call these Cayley tables in the language of the group theorist. So we want a multiplication table. Let's go up to here. 1 for 6, 21, 50, so 6, 15, 6, 15. So we really are just going back to what's the first thing you did when you learned about multiplication at school. You probably did a multiplication table or something like that. And in fact, in that Key Stage 2 paper, we had that Sudoku looking thing, you know, that was like basically a multiplication table. And then we get to degree level where it's like, okay, now we're not just talking about numbers anymore, we're talking about the things in the abstract. So binary operations on general sets. And here we are with a multiplication table. So it's like we're just starting again. Okay, it's like now you've had a flavor for what maths is, now let's really do it. I'm going to omit the notation for this before I bore everybody, including myself, to tears. So 6 times 6, take 21 is 35, sorry, 36, take 21, 15. 6 times 15 is 90, which is 6. Commutativity in this group, so we can just fill that in. what is that telling us? It's telling us that this is a subgroup because we've got the identity and it's closed, and we've got our inverses here and everything, so that's all good. 6 times 6 is the identity. We call that an involution, so where it's square to the identity. 9 times 9, take 21, gives us the 18. I'm going to go ahead and, well, we know that 15... In fact, I could have just done that. Yeah, what am I doing? I know that 15 is acting like the identity, so I should have been able to use a bit of shortcut there. I can fill these in because the 15 is acting as an identity. And now, since this is indeed a group, it is the case that we get different elements on each row and in each column. So that's just a fact. So that's fine. Find the inverses of all the elements in S. It is not necessary to write out the whole multiplication table for S. Is that instructions or is it a hint? Because we know 6 inverse is 6. We know 9 inverse is 18. And we know 12. We don't know 12 inverse yet. And we don't know 3 inverse yet. We know 15 is self-inverse because it is the identity. And we know the inverse of 18, 9, right? Yeah, is 9. So what happens when we do 3 times 12? We get 36, which I think this looks familiar. This turns out to be 15, doesn't it? So these are these are inverses of each other as well. And we're done. And we're done with that degree level paper.
Nice question. Like that one.
Oh, okay. So, now what is the question? Should we do that further maths paper?
Yeah.
Bite the bullet and get it over and done with?
Yeah, I think so. I don't think there's going to be any better time to do it than now, to be honest.
No, and I feel terrible, honestly. I remember last year, I just felt like I could keep going and keep going. This year, because I did not sleep very well and my back is sore, I just feel pretty naff. So let's just get it over with. I don't like... I did not enjoy the further maths paper last year. It was probably the paper that I enjoyed the least, really. Even though I usually enjoy the more complicated stuff. It's just messy, isn't it? You know, what did you describe it as last year, Dan? Like, further maths is...
It really does test your ability to keep a cool head. I can't remember how I described it, but
ugly.
You just... Yeah, they're always really ugly sums, and then they're always really ugly sums, and then in university level they kind of set papers that you get into a really ugly state, and then you go, oh, okay, this cancels, and the answer is 7. But in further maths, no, the answer will be like 3 plus square root of 27 over 4 times pi cubed, like that will just be the answer. Yeah. And you kind of go, well, that's not pretty.
Yeah, it's completely agree with you there. It's just just never nice, is it? I am actually gonna take a 10-minute or so break here because I haven't eaten anything since I had my breakfast. So I think I should probably do that. I think
agreed.
It's the natural point. We've reached the end of our mathematical journey. So that's what a degree paper looks like. I don't know. I don't really know what people will make of that. But that's.
I think I believe that it is you, me, and James currently watching.
Yeah, it is. Yeah, I just mean for posterity, this is going to be on YouTube for potentially forever. So we might have people watching this later.
I did also check part 1. Part 1 is saved and uploaded.
Oh, incredible! Yes.
Yeah.
I was very anxious about that because I tried to teach OBS to save the backup, but it just won't do it. So I don't know if it's like a storage problem or I don't know. So let's take a quick recess here. Let's say come back at 2040.
2040. Gotcha.
I'll be back in a bit.
We'll keep it warm for you.
Thanks.
So earlier on, Dan, I was talking to them. I was probably saying some fairly uninformed things about Piaget.
About who?
Oh, it's like a education theorist, like but primary stuff.
Right.
So I won't rehash all of that.
I'll watch it back in the video.
So,
but what I will just say that in that session, in that first session, we raised £320
Not
for
bad.
Refuge, which
Not
is very
bad.
good. We went from 385 to 705,
Cool.
which is absolutely amazing.
Yeah, it's good stuff. Really good stuff. A lot of generous people out there. It's really nice.
There is, yeah.
It's quite a few. It's nice. Like we had quite a few NHS people around as well. So.
Yes, I saw that in the first session also had 100 views, so this is great.
Oh wow, that's awesome.
Yes, exactly 100 views. I don't know if that's YouTube doing its counting. We all know that YouTube can't count very well with numbers under about 500.
Yeah, but no, I don't know. I think that seems plausible. Seems about right. Obviously, some of them it will be people dipping in and out or whatever. But cool.
Yeah.
And it's compelling viewing. I mean, I think it is like, yeah, it is kind of hypnotic. I think so. Cool. No, what I was going to say was like with the so we just saw that sets, numbers, and functions paper, right? So that's one like very important part of initiating people into the world of undergraduate maths, right?
Yes.
What were so at Manchester? What are the other first year courses?
So, on the pure side, you had sets, numbers, and functions, sequences, and series.
Oh, okay. So there's a
and then
separate
sets,
sequences
numbers,
and series. Okay.
And then either there was a sets, numbers, functions 2, or I'm wondering if real analysis was in.
I did real analysis.
You did real analysis.
I did
okay.
real analysis. So real analysis.
There was sequences and series.
Shall I look it up?
Yeah, probably. Yeah. And then on the applied side, I cannot remember what was the first semester.
Currently, oh wow! So sets, numbers, and functions doesn't actually exist anymore.
Really?
Yeah. So now for year 1, there's probability 1. Calculus.
Still Professor Moriarty?
Let me have a little look. It does not. Oh, Thomas Bernhardt.
Oh, okay.
And interestingly, they have David Sturzaker's probability book on the reading list, which I approve of. That wasn't there when I don't think that was one of the books when I was there, but that is a good book, the Sturzaker book on probability. That's interesting. And we also, so there's probability 1, calculus and vectors A. And I think this whole thing, the A-B thing, it's to do with whether you're doing joint honours or not, isn't it? So if you do,
yep, that's right.
So A is like the full version, and that's the one that has quite a lot of interesting stuff. So it's not it's called calculus and vectors, but it's got all the stuff about complex numbers in there as well, which I think is very interesting.
Yeah, because it's all about turning and rotations and.
Yeah, and it covers a lot of the content that will be repetitive for people who've done further pure 4, because it covers things like the cross product and that sort of stuff. But good. I really like that content. That's really good. Linear algebra A, which covers.
I liked that. I really enjoyed that
linear
course.
Algebra sound. I think everyone likes linear algebra, to be honest.
Everybody, yeah. Carolyn Dean, I think, was our lecturer for that.
Again, having done further pure 4 would be a huge advantage. Actually, looking at this, so you get intro stats, which is really a very introductory course. It's got just tests, hypothesis tests, supposing it looks like, and sampling. which are very important stuff. And then I think what used to be called sets, numbers, and functions has been subsumed into something that's called foundations of pure mathematics.
No, I think that's fair, because I was looking at the paper that Alex was doing, and I was thinking that like truth tables doesn't really fit into sets, numbers, or functions.
I mean, if you're being argumentative, you could say that it is kind of set.
Yeah, I know,
theory,
but it's yeah, but it's logic, right? That is logic,
Yeah,
course
sure thing.
0. Because once you get into like predicate logic and stuff, it really is, you do go back to truth tables and then you just take it to another level.
And interestingly, there's only one book on the reading list for that course, which is the Peter Eccles Intro Maths Reasoning book.
That doesn't surprise me.
Yeah, well, I mean, very.
It's a good book.
I've heard that. It's interesting. Like, I've not actually got that one. I've got Alan B instead, Numbers and Proofs. But
That was the Cambridge recommended one.
I actually think it might have been on just the John's list. I don't remember whether it was on the main university list, because John's had its own list as well. But either way, it was a first year book in Cambridge. And I really like the Allenby book, and I'd recommend it to anybody. But I maybe should get hold of the Eccles book and have a look at it one day. But yeah, interesting stuff. And then, so that's year 1. So sequences and series actually still exists as a separate course.
I hope it's still Alex Wilkie. Although he may have retired by now, but he was a wonderful lecturer.
It is Mr. Cole. Oh, sorry, not Mr. But it's Mark Coleman, apparently.
Oh, okay, even better.
Even better, yeah.
He was I really enjoyed his lectures.
Yeah, and then of course, Mathematical Workshop. You remember that?
Right. Yes. Which.
Well.
Less said. Less. That was the group.
Group stuff.
That was the group course that wasn't about maths.
Didn't they teach you LaTeX in it?
No.
Oh, they do now. So
okay.
Week 2.
Yeah.
Week 2 of your first year of university, you're learning. They're showing you LaTeX and saying, "Hey, this is a good thing to learn."
Actually, and MATLAB as well.
And MATLAB.
Yeah. Okay. No, I think that could actually be a lot more interesting, because we basically were given a hard problem, and then in a group of 4 of us we had to solve it. And then at the end of week 6 we had to, or at the start of the end of week 5 we had to present it, and it was often in that group project, one person would solve it, and then the other 3 would just stand there while other people would, while the person who solved it would speak.
I'm just having a little look at what else is there. So year 2 looks pretty similar to how it. Although the Python is there, mandatory Python. That's interesting. That's a good idea.
Yeah. Like, I really liked that MATLAB was in there, and LaTeX, because the first time that I used LaTeX was in the 4th year of university.
Yeah. No, but listen, there's like a 10 credit programming with Python in year 2 that's mandatory.
Good. No, I think that's really good.
Yeah, it's a great idea.
Yeah. Because, I only picked that up after university, and boy, I wish that I'd had someone to just, like, give me the confidence to be able to go and do it.
Yeah. And was probability 2 always mandatory? I don't remember.
Yes, it was.
Yeah. Of course.
It was. I can't remember who taught it in my time.
Peter Eccles taught it when we were there.
Yes. Yeah. Okay. Yeah.
Interesting.
I was never good. I was never good at it.
Well, it's one of those
Peter
things.
Eccles teach it?
I don't know. It's one of those things.
I do remember. I do remember. Peter Eccles taught it because he lost a bet.
Oh well, I let's not get into this. But as far as I'm concerned, it was a good course, and it what's the word? A lot of calculus, which I'm always happy with, really. Interesting what's happened to the third year courses as well, looking at it. So it looks like practical stats is not on the scene anymore, which is a shame because I really love that course. Maths Bio is still there, which was a really cool course. All the stuff about... Did you do Maths Bio?
No.
Oh, that was great. It was fairly eclectic, I would say. It had... So you got like a little bit of Markov chains. You got some like differential equations in there. You got a bit of history in there as well, because you got all the stuff about Turing and the sort of, the whole thing about patterns on animals, that kind of stuff.
All right, yeah.
So you got that like diffusion kind of stuff in there as well. That was a good course. I really enjoyed it. So that's there. But in terms of what's new, viscous fluid flow, I don't think that was there.
That was always there.
No, there was a fluids, which I did. I don't remember viscous fluids being separate.
I think it was in the second semester.
Oh, okay, fine.
From what I remember.
And then we have also new mathematics of a finite planet.
Oh, I saw that, and I've just clicked into it to understand what that is.
That's cool. I love it. What else have we got? We've got...
it's sort of touching life sciences.
I don't see that. Oh, generalized linear models is still there. That's good, because that was awesome. Green's functions. Yeah, I kind of regret not doing Green's function. Interesting.
All right. Hello, Alex. How are ya?
The available courses.
Yeah, we're just talking about what's different, what's the same. The first year's changed quite. Sets, numbers, and functions isn't a standalone thing anymore.
Oh, really?
Yeah. And also, I was sad to see that actually practical stats is no more.
Well, I'm not sad about that.
Well, I know you wouldn't be, but it was a great course. I mean, it was very different.
Wasn't that the course that everyone got 100% on? Because it was like coursework.
Everybody didn't get 100%.
Some people got 120%. Didn't they?
Okay. So there was bonus credit available in that course, right? So it capped off at 100, right? So you couldn't in practice get over 100, but some of us were able to get the 100 credit regular credit and all of the bonus credit, which was a nice feeling. But it didn't really matter, and the course wasn't like an outlier. It didn't make the course an outlier. There were probably more 100s than there were elsewhere, but like the overall distribution of grades for it wasn't outlying.
Yeah. Okay.
Yeah. The only thing new, just last thing to say on this, the only thing new that I could see in year 3 on the pure side was fractal geometry.
Fractal geometry, yeah, I don't remember that one. And this maths education one is new as well.
Maths education?
Yeah, 10 credit optional course run by the School of Education, maths education.
Oh, nice. I
mean,
I don't think I would have done it back then, but if I'd have known I was going to go into teaching, that would have been a great course to do.
I have to say the reading list for it is great. Richard Skemp. Yeah. Looks someone after my own heart is teaching that one.
Yeah. Adjust that volume a bit. Okay, so let's crack on, shall we? So further maths, paper 2, and I remember last year this was like I did 2 of the. I'm only doing 1 further maths paper this year because I got kind of bored. But it was so messy, so awkward. Don't know if they're particularly hard questions. There was a really hard Demoivre theorem question that I really struggled. I think it took me about half an hour to do last year. So hopefully nothing like that. But let's see what we got. Let's see what you got. So, in terms of what's on the further maths spec, I mean, complex numbers is on there. You don't see any complex numbers here in the vanilla A-level, do you? There's a bit more calculus, I think, but not much more. Matrices. It's changed as well since I did it, so we might see... What else might we see? Second order differential equations. Boy, I hope none of those come up, because yeah, not great at those. What else? More polar coordinates. Did you do polar coordinates at A level?
Yeah.
In normal A level?
Oh no, not in normal A level. I think that's
That's one of the
was-
things in further.
Oh, okay.
Yeah.
Further.
Polar coordinates then. What else? I think complex numbers is a pretty big. Yeah, it's a bit more calculus. There is volume of revolution.
You might get quaternions.
Quaternions. You're not going to get quaternions.
You get quaternions in further maths.
Not in this paper. I think not in this paper. The old FP3 maybe, but not in this one.
I don't think I met quaternions until I did undergrad. Personally, recursion, like those. I did actually revise this the other day. This is like we have a recursive formula. You have to find the formula for n. That I hope isn't on there because it's faffy. What else? Oh yeah, I was about to say, volume of revolution is on A-level maths. Surface area of revolution, that sort of thing, you know, arc length and all of that kind of stuff, I think is on further maths. Hyperbolic trig.
Yeah, hyperbolic trig. Yeah.
Okay. Anyway, let's go on with it then. So, come on, let's get this over with. A small sports club, only a small club. You know, nothing too crazy here. Just a small club. It's 12 adult members and 14 junior members. A club. Right, this looks like a combinatorics sort of question. Needs to enter a team of 8 players for a competition, but to determine the number of ways the teams can be selected if there are no restrictions on the team. Okay, I can do that. That's going to be 26 choose 8. Which the calculators still use this awkward C notation that nobody uses in real life. So quite a lot of ways to set up the team there. If the team must contain 4 adults and 4 juniors, so that's going to be 12 choose 4, and for each of those we can do 14 choose 4 juniors. So we'll do 12 choose 4, 14 choose 4, so 4, 9, 5, 4, 9. That's a nice number. And thirdly, more than half of the team must be adults. Okay, so you could have 8 adults, 0 juniors, 7 and 1. You could have 6 and 2, 5 and 3, and no further. You can't have 4 and 4 because it needs to be strictly more than half. I think that's right, isn't it? Okay, so there are, for the top case, 12 choose 8 ways of doing it, and then 12 choose 7 times 14 plus 12 choose 6 times 14 choose 2 plus 12 choose 5 times 14 choose 3. I think that's it. Hope the whole paper is as relaxing as this. I love a bit of counting. Okay. So we've got 12 choose 7 times 14. Do these all together. So 12 choose 6 times 14 choose 2 plus 12 choose 5 times 14 choose 3. So plus 3, 7, 2, 3, 7, 2. I find it amazing that we keep getting these like repeated numbers. Is that... should we expect that? Or 3, 8, 3, 9, 5, 5. Okay, does that make sense? So we've got, that's about 400,000, and that's about 15. Yeah, there's more, definitely, because there's 14 juniors, there's more examples of cases where there's more than half juniors, and then you've got the half and half. I can believe that. I can believe that. Okay, moving on. Oh, literally just said I don't want this to come up. I hate this. Right, luckily I do kind of know what I'm doing here. So what you do is this whole characteristic polynomial, a bit like doing a second order ODE, where you've got 9x squared, take 12x plus 4, and then you look for the roots. So hopefully it's a 3x, 3x. Could be a 9x and x. I actually think that. So we've got minus 6x minus 6x. So x equals 2/3. Okay, now what was the point in that? What you do here is... you've got your roots, a plus b something like that, isn't it? Something like that. And because it's a repeated root, I think we stick an n in there. And there's that as well to worry about. So I think I'm going to do... it's just like an ODE, isn't it? Something like that. And then I think you do... so you've got your... the solution. I know that you've got your particular and your general, so you need to do your particular solution plus the so the general solution plus the particular solution. And what you do is you say xn plus b is, sorry, an plus b, or xn plus y. I think you say substitute that in and get, that's how you get your particular, and then you use the initial conditions for the general. I think that's what you do, but I'm kind of winging it here because I'm not entirely convinced that I know what I'm doing. So that's xn plus 2 plus y, 9 of which we have there. So take 12 x n plus 1 plus y plus 4 xn plus y is equal to 3n. Okay? I wish I knew what I was doing. I literally, when I said I revised, I looked up how to do this because I knew, when I looked down the topic list, I knew that I used to know how to do these and I'd totally forgotten. So I remember looking at it and it's got some, it's something like this. Should have expanded that last bracket. Okay, so how many n's do we got? We got 9x take 12x plus 4x is equal to 3, comparing the n coefficients. So we get that x is 3. And then how many of the constants do we have? We have 18x plus 9y. Take 12x, take 12y plus 4y. And that is null because there's no constant on the end here. So we know that x is 3, so that helps. So 18x take 12x is 6x. 6x times 3 is 18. So this is all going to equal minus 18 when all's said and done. Then we've got 9 plus 4, take 12, y is minus 18. Fine. So we know 3n minus 18 is our particular solution. And now we use the initial conditions to find out what a and b are. Ooh, okay. Okay. So we know 1 is equal to a plus b times 2/3 plus 3 minus 18. And we know that 4 is equal to a plus 2b times 4 on 9 plus 3 times 2 minus 18. And then it's a simultaneous equations game. So 1 plus 8, so 16. Times it by 3 and divide it by 2. We get 24 is equal to a plus b. And on this side, 6. So 4 plus 18 is 22 minus 6 is 16 again. 16 times 9 divided by 4 is going to be, what's 16 times 9 divided by 4? Come on, brain, what are you doing? 36. A plus 2b. Okay. So this is telling us that b is 12. And it's telling us that a is 12. Okay. So I think 12 plus 12n times 2/3 to the power of n plus 3n minus 18. That is the answer that I've pulled out of my backside. Does any of this seem familiar to you guys?
Yeah, so because it's got a repeated root, that's why we've got the bn there, right?
Yeah, I remember the bn because
it's a repeated root. Just because it's just because the characteristic polynomial has a repeated root. I think that's
yeah. That's why I put that in there because that felt right. That's what you would do in an ODE, isn't it?
Yeah.
Because
Exactly.
Otherwise, you're essentially repeating the same information.
Yeah.
Which is you've essentially only got one constant there. Is the general sort of idea? Because I think the point is you have A and then R1 plus B R2. But if R1 equals R2, then you're not. Yeah. So the trick, and to be honest with you, I don't know why it works, but it just does. What do you think about that?
Yeah, I mean, this looks good to me, honestly. This is like, I agree with the characteristic polynomial. I agree with what you've done. I think you've done what I expected you to do with the initial conditions. So, yeah, I can't really speak to the actual numbers because my arithmetic's so dire. But
let's leave it there then.
Yeah, I think this is good, honestly.
Hopefully that's right. Okay. Oh, it's a matrix. So if I have another... I would like to think my specialty would be group theory after spending an additional 4 years doing a PhD in it. But I do like linear algebra. So this should be okay. So let's jump straight in. We've got show that in terms of K the characteristic equation for M. So that's the determinant of M minus lambda times the identity. So, in other words, we have got 1 minus lambda minus 4 minus lambda 3 minus lambda. K, that's interesting. We'll be solving for K later, no doubt. So the determinant of that, God, I haven't found the determinant of a matrix in how long? So 1 minus lambda, okay, and then we've got minus 4 minus lambda, 3 minus lambda, subtract 2, subtract K times 2, 3 minus lambda, subtract 1. Now, I always get this wrong, actually, because some people write this as plus, 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 but then they swap those two terms. So it's like that times that, but then for the middle one, it's that take that. But I always do it as an alternating sum. I don't know how about you guys.
Always confuses me every time whenever anyone would be writing that down, and then they would just swap two terms. I would be like, I have no idea what just happened. Why did you get rid of that minus?
Yeah, I'm a term swapper.
So you would do it like this.
You
would do it with that.
Yeah, I mean, I don't know. It's a long time since I've done this stuff, but yeah, I mean, I think
it is the same, isn't it? But
yeah.
Right, this is messy, isn't it? What were you saying before about ugly questions, Dan?
This one might actually be nice.
It should boil down nicely, shouldn't it? I mean,
in a couple lines, I think you'll be fine.
Yeah, we should see some fireworks.
Thank you, Ella. Thank you, Ella, as well for donating. I don't know if you're here in the stream, but thank you for that.
I didn't realize. Oh, thanks so much, Ella. I think Ella's actually already donated, so that's really nice of her to donate a second time. Thanks very much. Hopefully tuning in as well. I'm not sure how interested in the maths she'll be, but I'm not sure how interested anyone is. I think I'm with the only. I mean, we're in the only group of 3 people who are actually interested in doing this. So plus 4 lambda. I think that's right. A lot of minus signs in there. I wanted to make sure I got that correct. It's definitely 4 plus 4 plus lambda. Definitely 8 plus lambda. So times minus 2 is minus 16 minus 2 lambda. Happy with that. Right, so we've got to deal with this at some stage. 1 minus lambda. What I should have done is just pull a minus 1 out. That would have tidied it all up. Minus 12. Take 3 lambda plus 4 lambda is plus lambda squared. Minus 2 plus 2 lambda. Minus 6k plus 2 lambda k plus k. Take 16 minus 2 lambda. Boy, what a mess. Minus 12 plus lambda squared plus 12 lambda, take lambda squared, take lambda cubed, and the fact that we've got a negative lambda cubed is unsettling, but it equals 0, so it can times 3 by minus 1 anyway, so that's fine. Okay, so that's that part dealt with. Any of this tidy up at all? We've got a minus 18 floating around on the end, which is good, because I want a 30 in the end, and I've got a minus 12 there, so that'll add up nicely. So let me just keep really, really close track of everything we've got here. So I've dealt with that, and I've dealt with that. Any lambdas? Oh, okay, bit of cancellation. Not quite the fireworks we wanted, but it'll do. So that's minus 5 lambda plus 2k lambda. So I dealt with that. Okay. So let's start to bring this all together now. So minus lambda cubed is what I've got there. Now let's collate the lambda squareds. I've got a plus lambda squared and a minus lambda squared. Love it. Should I have any lambda squareds? No, I shouldn't. So that's good. That's good. And I've got lambda plus 12 lambda is 13 lambda. Take 5 is 8. Then I've got the 2k lambda. So I'm happy that I've dealt with that, I've dealt with that, I've dealt with that, I've dealt with that, and then I've got the minus 30. Now this is equal to 0. because the characteristic equation is that 0 is equal to that. So we can times through by -1. I'm sorry I'm doing this so painfully slow. It's just easier to get it right first time than have to repeat. So what form does it... So it wants me to pull the lambda out. So this is... Oh, that's magically transformed into a lambda. We've got how much lambda? 8 plus 2k lambda. Oh, okay. I'm missing quite a few terms here. What has gone?
Right. Did you include your -5 lambda?
Oh god! Even when you do it so painstakingly slow,
So the line that ends -18. You've got a -5 lambda that's underlined.
I know what I've, I know.
Oh no, that's
I've
fine.
muddled up my k and my lambdas here. So this whole thing here was that the 2 lambda cancel with that 2 lambda. That is a k -6k plus k. Oh, stupid. So now I've got that is in fact a 13 because I'm not subtracting 5. And I've got a -5k there, which becomes a plus 5k here. So now let's bring it all together. So that 13 lambda cubed, take 13 plus 2k lambda plus, and pull the 5 out, we get 6 plus k is equal to 0. Is that what it wants? Yes, but some of the terms are the wrong way around, but it's fine because by the commutative property, we've got it. Okay.
Nice.
Sheesh. That was a nightmare. Just long-winded.
Yeah, it is. I was going to ask, like, if you were the marker in this situation. And you see this and you read this because you've done marking of like university level papers where you will have a student that will just give you this. How do you decipher all of that? Like whether they've done it right or they've just gone, well, it just clearly equals the correct answer at the end, and I've just written a whole bunch of numbers and symbols down.
Yeah, it's hard, isn't it? Because you can't afford to just spend all day like staring at it. So it depends how these 3 marks are assigned. So you would hope. So usually you'd probably get a mark for getting as far as that, for knowing that you've got to define the determinant of that matrix. You get your second mark for that, and then you get your 1 mark for correctly tidying it up. But you know, it's how do you know if they've actually done it right? Are you really gonna like go through and unpick it? So usually there's like a checkpoint. Sometimes you get something like, you know, you get 1 method mark if they get something that looks about that stage. You know, but I don't know how this would be assessed. I mean, for 3 marks, that is a lot of work. I think I spent more than 3 minutes doing that.
Yep.
And I don't really know the quick way of doing it.
No, there isn't more. If you calculate eigenvalues all the time, you get quick. I think that's what it is. Right, I am going to drop now. But it's been lovely. Thank you for having me, and thank you to everyone who's watched and donated.
All right, thanks very much, James.
And best of luck. I'll check in the morning. All right, ta-ra. Cream is here with you now as well.
Oh,
so
hello.
Ta-ra. Bye.
How are we doing?
Yeah, I'm all right. How are you getting on?
Yeah, not too bad. We are on paper number 9. I deliberately spent more time than I needed to on the degree level paper just to explain a little bit more about what's going on. Because I remember last year everyone was just like, right now I'm completely lost. So
yeah,
I just wanted to talk a little bit about it. I've also done like a lot of the really easy papers, like the Key Stage 1 and Key Stage 2 papers.
Yeah, I've been watching you on and off
the
day. So yeah, no, it looks. Is there any logic to the order? Like there's no.
So there was. We did that string of of papers from key stage 1 all the way up to the degree level, and now the logic behind doing this one is that I think this is going to be the nastiest paper among the whole thing, so I just want to get it done and out of the way. And then I've got a bunch of I've got about 8 A-level papers and 1, 2, 3, 4, 6, 7 or so GCSE papers. So I'll leave a few of the easy ones for the middle of the night, I think, where I can just power through and get them done. But yeah.
So you saying this is the hardest just because you haven't prepared for it? Is it got new concepts that are?
It's just messy. So it's just the questions are just hard. This is the A-level further maths paper. It's just like this question here. There's nothing conceptually too difficult about that, but it's a lot of algebra to have to soldier through for 3 marks. You know what I mean? So it doesn't give you that much time and reward for doing quite a lot of even though it is quite mechanical work, it's just a lot of work.
Yeah, especially under exam conditions, I think.
Oh yeah, I mean, I think I'd need better stamina than I currently have now to be able to actually do one of these papers in the 2 hours. So we're doing a bit of matrices. So next part of the question, curiously, has nothing to do with the first. So we have got the determinant of this is equal to 5. So I need to do 1. So minus 12, subtract 2 is minus 14. Subtract k lots of 6, subtract 1 is 5. Minus 2 lots of 4, subtract minus 4 is 8. So minus 14, take 5k, take 16, and we know this is equal to 5, which is good because this is going to be 30. Minus 5k take 30 is equal to 5. So minus k take 6 is equal to 1. So k is equal to minus 7. Okay, now something to do with eigenvalues, I guess. I don't think eigenvalues. Use the Cayley-Hamilton theorem to find the inverse of m. Okay. Now, the only problem with the Cayley-Hamilton theorem is I have no idea what that is.
That's quite a problem.
That is a problem, yeah. What is that?
Matrix over a commutative ring satisfies its own characteristic equation.
Yeah, okay. That sounds about
What does that mean?
Thanks for clarifying.
What the hell is that?
Right, you know what? I'm going to cheat here, and I'm going to see if Mr. David Poole can help me out. So, if anyone is interested in linear algebra, this is genuinely one of the best undergraduate textbooks I've ever had the pleasure of thumbing through, because I've not sat down and read the whole thing, but it is incredibly accessible. So the Cayley-Hamilton theorem, 297. Okay, so yes, we know who Arthur Cayley is. Right, I love this as well. In true maths textbook fashion, it isn't like a chapter on the Cayley-Hamilton theorem. It is in the exercises. Oh, by the way, there's a really useful theorem that we can use here. We'll just teach it to you now while you're doing the problems. Amazing. So it satisfies, right, so it is saying that if you've got the polynomial in lambda, the characteristic polynomial, then it is saying that P of the matrix is equal to 0. And somehow that will tell us how to find the inverse. Okay, alright. So we did find the characteristic equation here, and we do know that k is minus 7. So we've got lambda cubed, so 2 times minus 7 is minus 14, plus 13 is minus 1, so take minus 1 plus lambda, plus minus 7 plus 6, so plus minus 5 there, I guess, equals 0. And then the Cayley-Hamilton theorem says that m cubed plus m minus, it's not minus 5, it'll be minus 5 times the identity is equal to the 3 by 3 0 matrix. Now, this can indeed help us find the inverse of m, because if I know that m cubed plus m is equal to 5 identities, then I know m times m squared plus the identity is equal, and if we divide both sides by 5. So in other words, m multiplied by 1/5 of m squared plus the identity is equal to the identity, which means that is in fact the inverse of m. So that's what it wants us to do. Now, we can invert a 3 by 3 matrix the old-fashioned way, but it is an absolute, talk about horrible questions, Oh, James does remember the Cayley-Hamilton theorem. I mean, I think I did know that. I just didn't know it by name, because this, as soon as I wrote that down, I immediately knew what to do. So I have used this before. So we just need to find a fifth of m squared plus plus the identity. So let's find m squared first. So we've got 1, 2, 1, k minus 4, 2, minus 2, 1, 3, times by 1, 2, 1, k minus 4, 2, minus 2, 1, 3. Okay, so a bit of the old matrix multiplication. Oh, and we know that k is minus 7. What am I doing? I'm getting very slow. I'm getting slow already. I'm not even halfway through. So, 1, take 14, take 2. Oh, jeez. I'm just not on it today, am I? So that's minus 15. Oh, and I was about to say that's good because we have to divide it by 5. But we are going to add 1 to it before we divide by 5, which is annoying. That's a classic further math thing we were talking about before, Dan, isn't it? Why wouldn't you make it so that it turns out nice, Anyway, minus 7, take 4 lots of minus 7, okay, take 6 is 15 again, minus 7 plus 28 is 21, take 6 is 15, minus 2, take 7 is minus 9, take 6 is minus 15. There's something not quite right here. I don't buy that they're all 15. So let's get the calculator. 1 take 14 take 2 is minus 15. Minus 7 plus 28 take 6 is 15. Minus 2 take 7 take... Oh, it's not take 6, is it, on that one? Sorry, guys. It's a bit tedious, isn't it? Like, there's just no quick way around it. That's 17. With such similar yet slightly different numbers, I was surprised that they all came out to be 15. That's what tipped me off. Take 7, take 6. That is minus 15. All right, okay. We'll have that one. So 1 take 8 plus 1 is minus 6. Minus 14 plus 16 plus 2 is 4. Now that is going to be nice because we're going to add 1 and divide by 5. And then minus 4 take 4 plus 3 is minus 5. 1 plus 4 plus 1 is 6. Minus 7 take 8 plus 6 is minus 9. Minus 2 plus 2 plus 9 is 9. Okay. And you know what? I think my calculator actually does this. So matrix A is 3 by 3 and it's 1 minus 7 minus 2. Completely forgot that I had this function on my calculator. 1, 2, 3. Okay, equals that. So matrix A squared equals minus 15, 17, minus 50, minus 5, 4, minus 5, 8, minus 9, 9. Wow. Even with the calculator, I did that so wrong. how did I get it so wrong? Yeah, I can see where I made the mistake there. I did that times that instead of that times that. Just awful. So, anyway, can we please end this question? So, minus 14, 5, 10 on the diagonal. 17, minus 15, minus 5, minus 9, 8, 5. And then we need to divide the whole thing by 5. So we get minus 14 on 5, 17 on 5, minus 3. 1, 1, minus 1, 8 on 5, minus 9 on 5, 2. That is the inverse of M. Oh, I feel like I've aged about 14 years answering that question. Right, moving on. Could use my calculator to check the answer, but let's not. Let's just move on.
Calculators were allowed in these papers, right?
Yes, they are. Provided they can't store text is always the caveat.
Right. Yeah. Because I always remember, like, I had a big blue Texas Instruments calculator that could basically answer any question that I threw at it. It was a mini Wolfram Alpha.
Right. Could it store text?
Oh, hell yeah.
That's not allowed. Okay, so starting to lose my voice now. Figure 1 shows a sketch of a design for a road speed bump. Cool. The speed bump has a uniform cross section. Okay, yeah, and it's modeled by that polar equation. Okay, yes. So I can already tell this is going to be one of those surface area questions. So the units. Now I do actually have the A-level formula book here because I think I know them, but I'm going to need some of these from the formula book. So I'm going to pull this from the formula book. Arc length is equal to the integral of root r squared plus dr by d theta squared. That's the faffy one. That's the tough one, isn't it? Remember this. So because we're going to need the length of that times by that to find the surface area, and we're also going to need the integral of area under what is the polar area is half times the integral of r squared d theta. I think that's right. I'm going to check it in the formula book though, because why not? Because this is definitely a question we don't want to get part way through and then realize we've done the wrong thing. Yeah, okay. And if I had, yeah, okay, that's fine. So the area of this whole thing is going to be 2 of those because we want the flat surface here, and it's going to be the arc length times 2.35. Well, it'll be the arc length, that's 235 centimeters, because this is in centimeters, which is awkward. So I think that's the overall strategy for this. I think we've just got to do it. So r squared, first of all, that is going to be 900 1 minus theta squared squared, which is 900 1 minus 2 theta squared plus theta to the power of 4. Interesting. I'm not going to expand that out. I don't think I need to. Now let's do some other bits and pieces before we start putting it all together. dr by d theta. So that's 30 minus 30 theta squared. So dr by d theta will be minus 60 theta. So, okay, let's do this one first. So area of these shapes, these kind of almost semicircular bits, are half times the integral of 900 1 minus 2 theta squared plus theta to the 4th d theta. And you know what? Because we need 2 of them in the end anyway, I'm going to just do that. And then I get 900. And we are integrating between 0 and 1. My favorite 2 numbers to integrate between. So this is going to be theta minus 2/3 theta cubed plus theta to the power of 5 on 5. And because we're integrating between 1 and 0, we just do when theta is 1, because the 0 case it dies. So this is 900, 1 minus 2/3 plus 1/5. Alright, into the calculator we go. 1 minus 2/3 plus 1/5 is 480 for the end caps of the shape. Now the hard bit is this here, because this can sometimes turn out to be a complete nightmare. So let's do it. So we need r squared plus dr by d theta squared. Now r squared is that 900. Now I am going to expand it because it's going to interact with this. Take 1800 theta squared plus 900 theta to the power 4. And I'm going to add it to, well, 60 squared is 3600 theta squared. Yeah? So this becomes 900 plus 1800 theta squared plus 900 theta to the power 4. And let's pull the 900 out again, because I think I know what's coming. And this is actually a very nice question, so thank you for that, because here we now get factorize is just 1 plus theta squared. 1 plus theta squared. In other words, 1 plus theta squared squared. So this is 30 squared times, so this is, now the reason I'm doing this is because we need to root it, which means we need it as something squared before we take the root. So when we now root this whole sucker, we are going to get the integral between 0 and 1 of the square root of that, which is just that. So this is probably the nicest version of these questions I've ever seen. It doesn't always happen so nicely, and it can sometimes get really messy. So this is 30 times, well, I can just go ahead and integrate. Theta plus theta cubed on 3 between 0 and 1. So it's just 30, 1 plus 1/3. So 30 times 1 plus 1/3 is going to be 40. I suppose that makes sense, because that's 4/3 times 30 is 40. Yep. So this is 40. And then we times by 235. So the area of this top part here is 40 by 235, which, in case you forgot, that's the whole point of doing all of this, is 9,400. So the total area will be 9,400 plus 480 is 9,880 centimeters squared. Oh, you know what? That felt really good. That
About as good as it gets.
Yeah, that all just worked out really nicely there.
The only thing that I'd say that I didn't like about that question was that there was a lot of multiples of 100 with a theta in there, and I would certainly have lost track of what's a 0 and what's a theta.
Yeah, and my handwriting with a very inky pen doesn't really help, does it? I mean, some of these...
There are a couple of zeros that look like halfway between thetas and phis, but yeah, you got there. You got there. Very, very, very happy, and you saved a lot of paper.
Yeah, I know. Well, I was saying this before. Like, I really wish that I had looked. I didn't want to look at the questions. Is the problem? So I Because even if you glance at a question, you think, "Oh, I know that that's on it now." So I didn't even want to look at it. But now I regret it because I've got so much wasted paper.
I liked these questions.
Oof. So, this is some complex numbers. So we haven't come across the old complex numbers yet. So for the uninitiated, we can square root numbers. So the square root of 4 is 2. But you start to notice if you take 2 and square it, that's 2 times 2, which is 4. And if you take minus 2 and square it, that's minus 2 times minus 2, which is 4. So it's positive in every case. So traditionally, you can't take the square root of a negative thing. But with complex numbers, we just say we can. Let I squared be minus 1. Just say that it is and see what develops. And what turns out to happen is this is actually the thing that completes the number system. So we start with the notion of positive integers. We realize that there's some equations that we have to solve that involve negatives. We are all very comfortable with the idea of negatives for some reason. I think just because we learn them so early, we get very used to the idea, even though it's a completely counterintuitive idea. You know, just because you can have 3 apples, why is it you can have minus 3 apples, you know? And then you need rationals, you need irrationals, and then complex numbers turn out to be the thing that actually finishes off everything you could need from your number system. So it seems like a very unnatural thing to do, but by doing it, you end up with the most glorious, you know, kind of theory of numbers that you could hope for. Anyway, we've got some stuff here. So the circle with this equation is mapped to t, so mapped by t, which is this transformation here, onto the circle C. Eesh. Okay. So W is 1 minus 3z over z plus 2i. I is the imaginary unit. I think what we'll do is we will make z the subject of this, add I, mod it and set it equal to 3, and see what happens. That's what my gut is. It's been a long... I did not revise this at all. I thought my knowledge of complex numbers was... I was confident with that. Although, a few questions ago, I said my specialty was group theory, and I said if I had a second specialty, it was linear algebra, and then I didn't even know what the Cayley-Hamilton theorem was, so... Who knows anymore what I should be confident with and what I should not be confident with. Anyway, let's make Z the subject.
You knew it, just not by name.
Yeah, kind of, yeah. That's a generous way to put it. So, WZ plus 2I, W plus 3Z is equal to 1. Therefore, Z, W plus 3, and I like that because we've got that W3 plus 3 there, equals 1 minus 2iw, so z is equal to 1 minus 2iw over w plus 3. That's fine. So now we need z plus I, which is equal to 1 minus 2iw over w plus 3 plus I over w plus 3. Let's make the denominators the same so we can add them together. We've got 1 minus 2 wi plus wi plus 3i all over w minus plus 3. So that goes to 1 minus wi plus 3i. I'm hesitating because I'm just trying to look ahead. So therefore mod z plus I is equal to that over that. Oh, it's equal to 3. Yeah, that's the piece I'm missing. It's that, isn't it? So this is equal to 3. So in other words, that we'll factor out the I here. So plus 3 minus wi is equal to 3 times mod w plus 3 as required. All right, that was fine. Hence, find a Cartesian equation for C. Why would you want to find a Cartesian equation for C? The whole point of doing it in a complex plane is it's so much neater to represent things like circles in the complex plane, but a Cartesian equation makes things awkward. Never mind. Center and radius. Okay. So I don't think there's anything for this except. I think what we just do here is let w equals x plus I y. So a complex number, so normally we think of any old general number as x. A complex number is two of our usual numbers added together, but we times one of them by I. So it's got this real part and this imaginary part that we invented in the previous question where I squared is -1. So that's why I'm doing this, and I know that 3, sorry, that's a bar, so x plus 3 plus I y is equal to, okay, so 3 minus w I. This could potentially get hairy. Okay, so this is 3 minus x minus I y. I'm adding 1 and timesing up by I. So, sorry, bars is equal to 1 plus. So this is 3i minus xi minus I squared y. I'm going to do this in all the steps because this is where we could make mistakes. So 3i minus xi, now I squared is -1, so this becomes plus y. Okay, and let's split it up into the real and imaginary parts. So we've got 1 plus y plus 3 minus x I. Okay, so that is equal to that. So we have got 9 root x plus 3 squared plus y squared. Really? Yeah. Sorry, that doesn't, it's 3 on the outside, so it's a 3. And then we've got root of 1 plus y squared plus 3 minus x squared. But the roots are fine because we're just going to square both sides. So I get 9 x plus 3 squared plus y squared equals 1 plus y squared plus 3 minus x squared. Are you really telling me, are you really asking me to expand and simplify that whole thing? You are, aren't you? You are a pesky paper. Seriously? Fine. You win. You win, as always. So x squared plus 6x plus 9 plus that is equal to 1 plus 2y plus y squared plus 9 minus 6x plus x squared. So I've got 9x squared. Take that x squared over. That's 8x squared. I've got 9 times 6x. So what is that? 54x. So plus 60x. Oh, it's not even going to be nice, is it? You know? 9 times 9 is 81. Subtract 9, subtract 1 is 71. Are you joking? Oh, honestly. 8y squared minus 2y is equal to 0. Right. Genuinely going to be a mistake here. So I've dealt with that. I've dealt with that. The 6x, that all compiled together from that. I got the 81, the 1 and the 9 to create that, 71, don't even get me started on that. And then I've got the 9y squared and the y squared to get the 8y squared. I brought the 2y over. Okay, so we're all present and accounted for here. Right, okay, so one thing we could do is divide everything by 2. This 71 is an absolute pain. But
Is that 71? Is that 71 right?
well, 9 times 9 is 81, take 1 is 80, take 9 is 71. So as long as I've done everything right up to here, then I'm pretty sure that's right. Well, it might change. You know what? You know what? After we complete the square, it might turn out nice. Let's see. So plus 30x plus 4y squared, take y, plus 71 on 2. Alright, I don't mind one little measly fraction out here. So I have got 4x squared plus 15 on 2x plus 4y squared minus y on 4 plus 71 on 2 equals 0. Now to complete the square. So x plus 15 on 4 squared minus 15 squared on 4 squared plus 4 of y minus y on 8, sorry, 1/8 all squared, subtract 1 on 64, and that whole thing is times by 4, by the way. So that's 71 on 2 is equal to 0. And now expanding and simplifying, so 4x plus 15 on 4 all squared. Alright, time for some calculator, because this is just starting to do my head in now. So we've got 4 times minus 15, oh no, be careful. So 15 squared divided by 4 squared is that times by 4. So we are subtracting 225 over 4 plus 4y minus 1/8 squared, subtract 1/8 plus 71 on 2 is equal to 0. So
Are you subtracting 225 over 4 or 225 over 16?
I've times it by 4 here, so it is over 4. But
You've taken it out of the bracket, right? Yep, I got it. With you.
That's fine. 1 over 8 plus 71 over 2. Please be something nice. Oh my goodness me. Disgusting, isn't it? Just look at that.
What even is that? I can't read it. Sorry.
Minus 167 over 8. So this is 4x plus 15 on 4 all squared plus 4y minus 1/8 all squared is equal to, well, let's divide through by 4 now. So it's going to go to over 16. So 167 over, over 32. Okay then, fine. So center is at minus 15 quarters 1/8. Radius, root that. What an awful...
Cannot, no, it can't. That just can't be true. There's never been a circle like that in the history of the world.
I mean, does it root to something nice? No, it roots to root 334 over 8. But you know what? I'm done with this. I'm not gonna even bother checking the mark scheme.
Was there a time I remember a time when I enjoyed questions like this? Do you remember a time when you enjoyed turning the handle?
Well, you know, I make a big stink about it, but you know what? I enjoy all the questions. Apart from the trapezium rule, I enjoy them. Even questions, I find it quite relaxing actually, a question like this, because you are just turning the handle, but you know what I mean? It's like some people do mindful coloring, don't they, where you don't really need to think too hard about it. It's just kind of nice, so you have to think just enough to keep your mind engaged. Whereas for me, it's doing algebra like that, which is like really kind of quite sad, I suppose. What on earth is going on here? This was like a groups question. Figure 3 shows a plane. Alright, so it's going to be some kind of planar made up of regular hexagon and equilateral triangle joined to each edge with alternate equilateral triangles shaded. The symmetries of the shape are rotation. This is groups. Wow, they've put a bit of group theory into the further maths. Now, I was told about this, but I thought this was only a part of the additional pure maths module that you can do as part of further maths. So I spent a week in my training year in my old sixth form at Runshaw College, and I was speaking to the teachers there, and I helped with a lesson on, it was on Fermat's little theorem, and it was on groups. So, and since it was my, groups are my bread and butter, I could help out with that lesson, which was a really nice opportunity. And it was with my old A-level teacher, which was great. Absolutely love that guy. So I was aware of some of the trickling down, but I wasn't aware that it trickled down quite this much. Anyway, pleasantly surprised by this. This is probably going to be, I'm relieved that this is here actually, because I'm probably going to find this quite easy. I say that now. Let's see what happens. Okay, so we've got a permutation there. So the symmetry of the shape represented by that. So 1 goes to 3, 2 goes to 4, 3 goes to 5. Yeah, okay. So this is a rotation. 2 by 3 anti-clockwise, I guess. Don't know how else you would say that. B, write down in similar two-line notation the remaining elements of the group G. Oh, way to kill group theory, man. Oh. Really? Do we have to? Right, so I'm trying to fit the whole question on here. So we don't need to see that first one. What we do need is, I'll just sketch it again. We will do a little sketch here of these. So 1, 2, 3, 4, 5, 6. So this is what we're working with. So if you're not familiar with groups, a group, we're basically saying, how can we change the orientation of this shape and keep it the same? So an easier example would be something like a triangle, and label it 1, 2, 3. I can spin that triangle around so that it now looks like this, and we've got the same shape again. I could also have reflected it like this. So like if you're putting a mirror in the middle and you create that, and it's the same shape again. And it turns out that there's 6 possible orientations of this. With this, there's also going to be 6, because this is isomorphic to this, really, isn't it? Because we can't do a 6th turn, because then we get the shaded bit there, which isn't the same shape. So this is an S. This is S3, really. This is symmetric group of order on 3 objects, or Sim3 if you prefer the grown-up notation. But yeah, so we've got the remaining elements to work with here. What I'm going to do, I'm going to cheat here instead of doing them all in this 2-line notation. So the first one given to us is that. So what I'm going to do is I'm just going to list where we map 1 to 6 to. So we could have the group that we could have the element where we're mapping to 5, 6, and 3 goes to 1. So 2, 3, 4. So that takes care of the rotations. Now there's the reflections. So if we reflect it, then 1 and 4 stay the same, and then 2 and 6 switch places, 5 and 3 switch places. And then I guess the trick to rotating it is you just add 2 to all the numbers. So add 2 to that, you get that. Add 2, add 2, add 2, add 2, add 2, and then add 2 again, which will give us that, I suppose. Yeah. Okay, so these are the 5 non-trivial elements, and then there's the identity. So the do nothing transformation is the identity element of the group. Okay, explain why each of the following statements is false. G has a subgroup of order 4. So by Lagrange's theorem, one of his many theorems, but in the context of group theory, it only means one thing. If H is a subgroup of G, we use that notation, then the order of H divides the order of G, and 4 does not divide 6. So we can't have a subgroup of order 4, we can only have subgroups of order 1, 2, or 3. Or 6, you know, it's a subgroup of itself, I guess. G is cyclic. Okay, so why is G not cyclic? Well, I'm going to say G is isomorphic. Isomorphic to Sim3, which is non-abelian. To be a cyclic group, you must at least be abelian, so G is not cyclic. Now, that's a very high-powered way of saying that. I think if you want a lesser-powered way of saying that, you could say something along the lines of it's just not abelian, or you could say a rotation can only generate so much, a reflection and you know what I mean? Like, you can't generate the whole thing with one element. I don't exactly know how much detail it wants me to give for that, because I'd have to look at a further math mark scheme, but I think my answer is sufficient. Okay, diagram 1 on page 23. Jeez, there's 23 pages to this thing? Okay, diagram 3, page 23, diagram 1. The same outline as the shape. Shade the shape in diagram 1 in such a way that the group of symmetries of the resulting shaded shape is isomorphic to the cyclic group of order 6. Okay, so we want 6 rotations to be generating, so we want to generate it by a rotation. So it needs to have order 6 rotational symmetry, but we don't want it to have any reflective symmetry, because that would then double the order of the group, and it would actually be a dihedral group is what we call it. So what do we do here? I think if I just like shade in a bit on each of the triangles there to make it a kind of throwing star type thing, you could probably do something a bit more elegant, but that's the thing that I'm thinking of straight away. What do you think, Dan? Maybe something like that.
Stepped out there for a second. Felt like you had this in hand.
Well, yeah. I wondered if there's a neater answer to this. Maybe something like that. So like a throwing star type thing. So it's going to rotate around. It's got 6 symmetries going that way, and 1 generates all of them, but no reflective symmetry. So you're not going to, go above the order of 6.
Yes.
I take it you're...
Yes. Yeah. Yeah. You can't. Yeah, you can't reflect that. I think that's all you would need.
Oh, this looks horrible. This looks absolutely horrible. This looks like the exact kind of question I was afraid of. So in is equal to that integral. Show that. Jeez. Oh dear. For only 5 marks though, so it should be...
Is this an induction?
Well, I think it's basically asking us to do the inductive step, isn't it? And that is kind of the feel for what it will be. Okay. So I n plus 1 is equal to the integral of 4. I'm going to change this to over 4 minus x squared to the power of n plus 1 dx. And we've got to show it's equal to that. It looks a bit bipartsy, actually, doesn't it? It looks a bit bipartsy. It looks like we're going to have uv and then some change and then the integral again. So I'm going to make a note of that. So because I was talking to James about this before. This is the kind of calculus where I'm not as hot as I would like to be. So this is 4 over 4 minus x squared to the power of n times 4 minus x squared dx. Okay, alright, and then we can do 4 times the integral 1 over 4 minus x squared to the n times 1 over 4 minus x squared dx. Okay, now I'm getting biparts vibes from this, because this is in. So all we need to do then, right? So biparts, we want to do if we do u dv, then in our biparts we'll have u times the integral of that, which seems fine, and then we'll be subtracting the integral of the derivative of that times the integral of that. If we did it that way around, u dv, u times the integral of that, which I'm not really sure we can do, and then minus the integral of the integral of that. Okay, so I'm thinking that this is giving me yeah, I don't much like this. Let's just do it. Let's see what happens. 1 over well, let's put it back in this kind of notation, and dv is equal to 4 minus x squared to the minus 1. Du therefore is minus n times minus 2x times 4 minus x squared to the minus n minus 1. Okay, so it's 2xn over 4 minus x squared to the power of n plus 1. Okay, I don't want n plus 1 now. I'm trying to get in back involved. And then v, well, that isn't actually even a thing, is it? I mean, what is that? So if I've got 1 over 4 minus x squared, that is like a frigging that integrates to tan, does it? And we don't have any tans in here. So what on earth is going on? Because this is clearly not the way to. I didn't feel very confident about this going in. Oof. I've also got this 4 here, and that isn't even in the question. So what on earth did that come from? Right. Okay then. I don't see any way of escaping the fact that we're going to have to integrate that at some stage. And you can't. Because the integral of that depends on what n is. It's not a matter of, differentiate or integrate that. it depends, because it can go to a log, it can go to a trig, it can go to a straight up polynomial, and I don't see anything nasty in here, which leads me to think that this is just absolutely not the way to go, because when we integrate this, or if we do v du, then we have to integrate that anyway. Ooh. Sorry, well, yeah, when we do dvu, we have to integrate that in order to by parts it. I still can't escape the by parts of this. This stinks of by parts. Can we do something clever? Can we do something clever? Some kind of Mark Coleman game with this and do by parts on that. Can we split this up into two things times together and by parts that? Because starting from in plus 1, I don't see a way around this without having to integrate that. And if we're going to have to integrate that, we might as well just integrate that and show what happens. Because I think this is a recursive sort of thing. So if you integrate, I think what you're going to get. In fact, yeah, I think starting with that is the way to go, because we've got 1 over 4 minus x squared to the n. Generally speaking, when you integrate, you're going to end up with an n plus 1 on the bottom, because it's the denominator is going to increase in its power, which looks like in plus 1, doesn't it? So I think we just need to figure out how we're going to deal with that. And I'm thinking if we can do something clever with breaking this up into an appropriate u and dv in order to by parts it. I'm convinced that it's by parts. I just don't know the clever way of splitting this up. We want to split it up in such a way that we don't have to integrate it. That means we want the meat of it to be our u, and then we can differentiate it, because we can differentiate it easy enough to create our du, and then we make our dv something nice, and then we integrate that to create v. So what can we split this up into? Because the problem is, even if you do n minus 1 and then you have to integrate 4 minus x squared, we're still ending up with like tan or even is it than that becomes. I have to check the formula book, but it's nothing that we've got here. You know. What have they done? They've ended up with uv. So I'm going to cheat and kind of, well, it's not cheating because it's showing us, you know, we are given a clue here. So their uv, they've still got so their v turns out to be, if it is indeed by parts, 8 over 8 x over 8n. So in other words, their v is just in the order of x, which means they're, I think I know what to do now. I think I know what to do. It is something clever. This is exactly the kind of Mark Coleman trick. We are going to integrate 1 times 1. Yeah, it's clear to me now. We're going to integrate that. Right. Okay, I think this will work. So, sorry if all that babbling meant absolutely nothing. I was just trying to think out loud there. I think this will work. So, dv is 1, v is x, u is this old thing, and then du is minus n times minus 2x, so 2xn, 4 minus x squared to the minus n minus 1, which we note is equal to 4 minus x squared over n plus 1. So we're starting to get that in plus 1 involved. That's good. new piece of paper before we bring all this together. So, uv x 4 minus x squared to the minus n. I do remember doing this trick before, you know. It's not the first time I've done this. This is definitely a thing, because you're by doing it by parts, you're essentially avoiding having to integrate that, because the only thing you've got to do to that is differentiate it, which you can do. So it definitely feels familiar. Don't know where this 8n is coming from yet, but we'll see. We'll see. So we're now going to subtract the integral. We started with u dv. So we now go to the integral of v du. And oh dear, this looks bad. This still looks, yeah, I actually don't think this is the way to go now that I've looked at it. So 2x squared n over 4 minus x squared to the n plus 1 dx. Now that I've seen that, I'm immediately kind of, it's definitely that, and it's definitely that, isn't it? Yeesh. Because this isn't as clean as I wanted. It's not as clean as I wanted it to be. Getting a headache. Let me check that differentiation. So u is equal to just chain rule. 2xn is that what I had before? Oh yeah. What an awkward question. Right. I wonder if we can do something else clever with this. Let's pull the 2n out. So it's x squared over 4 minus x squared n plus 1. Can't be the way you're actually supposed to do this question. Like, this is the most unfriendly thing. What do we want? What do we want? We want to have somewhere in here, we want to have the integral of 1 over 4 minus x squared to the n, or to the n plus 1, because we can rewrite that as in. So that's what we want. We also want some 8n getting involved. We also want oh, jeez. How do we get rid of that x squared? Things that look like that are fine. Ooh, okay. So what if? Oh, this is another. Okay. I think we're back on.
By parts?
No, it's not another by parts. I suppose we could. Well, we could try another. We're gonna have to do by parts twice more on this to get rid of that 2x squared. I think I've got an idea. I think there's another Mark Coleman trick here. So what I'm gonna do, because that cancels to that if there's a 4 minus x squared up here. So, what do I mean by that? What I mean is, we've got all this stuff here, minus 2n, the integral of. Now, if I make this negative x squared up here, and add 4, and then take away 4. So this is the Mark Coleman trick at work. And now this, we can split into that and that. Okay, dx. And now that cancels with that. So it's coming together. We've got 4 minus x squared to the n plus 2n times, now let me just do these separately. So I've got 1 over 4 minus x squared to the power n, subtract 4 times the integral of 1 over 4 minus x squared to the power n plus 1 dx dx. That is x over 4 minus x squared to the n. I think up to this stage I've done it the way that they've intended, and beyond I don't think this is the right way to do it. This is ridiculous. I think I got lucky here. This is now in minus 4in plus 1, because that's in as we originally had, and that's now in plus 1. Okay, that is in. So now all we need to do is rearrange for in plus 1. So we have got 4. Sorry, we've got 8. There's our old friend, the 8n. We've got 8n in plus 1 is equal to, so I'll take that over there, take that over there, 2n in minus in plus x over 4 minus x squared to the power n. Then I'm going to divide through by 8n. Before I do that, let's take that 2n minus 1 out, in, divide the whole thing by 8n, and I get that. Now, is that anything close to what they've got? Okay, we're looking pretty good. So x over 8n, 4 minus x squared, 2n minus 1 over 8n. Yes! Wow! What an annoying question. What a horrible, horrible question. I feel sorry for any student of 2020 who had to sit that exam. Or were they cancelled due to COVID? I think they were cancelled.
Yeah. No. Oh, yeah. First year. Yeah, they would have been.
That is absolutely,
but someone.
horrendous.
There's someone there that wrote that paper, and thought, "Oh, I'm gonna get all these kids."
Yeah.
In that voice,
and then a mustache twirling exam writer who hates children.
Yeah. Yeah.
That was horrendous, and I got very lucky there. I was actually close to giving up. I think if I thought I had solved it when I spotted that, but then to also bring in that, I'm interested to see the mark scheme. I wonder if there's a piece of maths that you get taught at further maths A level that I've completely forgotten about that does make that actually a lot easier. Because to expect, I only know this kind of thing from real analysis. Do you remember real analysis, Dan, where everything was always, the reason I'm calling it a Mark Coleman, he was our lecturer.
At 0.
Yeah. Well, I'm going to add 0, and what I mean by add 0 is I'm just going to add 4x over 5, take 4x over 5. So I've just added 0, and that's what his number theory is. I'm just going to times by 1, but by times by 1, I mean I'm going to times by 4x over 4x, and that's the thing that makes it all work. It's like that. I, as a student, I'm telling you now, I would have not have been able to do that. So let's put this question to bed. For 5 marks.
Have you seen the comments in the chat from Jane? Checking you've seen it.
From my mum.
Yeah.
They give great tutorials. Preston's quotes on the donation. Oh, right. Did you hear what Preston wrote before on the donation thing?
Yeah, I'm glad I got that. So ridiculous.
So good.
It's also nice. So what he's done is did he do it in 4 chunks? So he didn't take James off the top donation spot. I wonder if he's done that as well.
Yeah, I think maybe that's what he did. Which that's just so nice, isn't it?
Preston.
So,
Yeah, very nice.
So Preston, what an absolute hero. So, although it did mean that all 4 of the slots were taken up by Preston, so it's a bit of a power move from him actually, like having 4 Prestons just there.
Yeah. Actually, on that theme, you've also got another tenner from anonymous person.
Oh well, thank you, anonymous person.
It's probably Preston.
Yeah, just stacking up. Right, I wonder if James has any insight into this. I remember doing tons of these questions age 18 or so. I don't think there is any trick, just practice. Well, what I used here, I think I would actually consider 2 tricks. You know, the tricks of this and this adding 0 business, you know, they are not natural steps to take. You know, especially this. Maybe if you've been practicing loads of integration, you get used to the idea that sometimes that is what you have to do. And once I realized that, I was like, yeah, I do vaguely remember doing that. But this trick of the adding 0 bit, yeah, not a natural step at all. Okay, so I2 is when n equals 1. Before I shoot myself, I want to finish this question. So this is x over 8 4 minus x squared plus 1 over 8 I1. Okay, so now all we need is I1. I'm actually using a lot of the paper given to me for this question because, boy, is it horrendous. So what is I1 then? I1 is the integral. I've lost it amongst my papers. So the I1 is the integral of 1 over 4 minus x squared dx. Now, as I mentioned before, I'm pretty sure this is a hyperbolic tan derivative. So I think this will go to... Right, let me think about how you do this now, because I always bodge these. So I write it like that is how I do it. Okay, and that's x on 2 all squared 1 minus all under 1 all times by 4 all integrated. So that is how I do it. So, and that is a quarter. Is it? Oh, I'm gonna have to check the formula book here. It's embarrassing. I should know these. I should know them. I'm sure it's tan. 1 minus x squared is, yeah, it's inverse tan, or tanch as some say it, of that. Okay, fine. And I guess we've got a plus a constant on if we're doing it properly. So we end up with I2 equals x over 8 4 minus x squared. If I have to write 4 minus x squared in brackets one more time, honestly, and equals 1 on 32 inverse tan x on 2 plus c. Wow. Never want to look at that again. That was horrible. And to think that's only 8 marks. So they are predicting that you can do that in 8 minutes. How long did that take? Half an hour?
That was a long time, yeah.
It was a long time. You felt it more so than anyone.
I'm just saying you could have done it a little bit quicker, actually. That was all I was thinking. Daniel's left the chat, by the way, so
All right, okay.
I don't know if he's had internet problems or just left, or he just got so sick of that question as well. He just decided to leave.
Yeah, I mean, it would not surprise me, and I wouldn't blame. Oh yeah, he says he's gonna drop. So, James is asking if I'm all stocked for food. I love that people were sending me food last year. It was really nice of people to do that. But I felt so terrible in the morning after eating. I think I had a box of chicken nuggets, a KFC, and a Domino's. So it's just like, you know.
I also remember like 15 minutes being wasted from. I think Emily ordered something and you just had a massive confusion with the driver.
Oh yeah, I had to go outside and like try and find the. And then the same thing happened with the Domino's at about 3 a.m. Okay, fortunately, there is only one more question. Oh, right, only 8 questions. It's like the good old days where you only get like 8 to 10 questions on a paper. On the actual A-level, you get about 14 questions now, which is just insane. So we have some number theory. So this is a nice surprise as well. So this is actually going to be very similar to the math that we were doing on that first year degree paper a little bit earlier on. Okay, now I can tell right now I'm gonna love this question. I'm gonna unashamedly love this question. So we've got a 4-digit number, and its remainder after dividing by 7 is 3. It's divisible by 9. Its first 2 digits have the same sum as the last 2 digits. The digit B is smaller than any other digit, and the digit C is even. Use property 1 to explain. Okay, so it's holding our hands a little bit to explain why 6a plus 2b plus 3c plus d is congruent to 3 mod 7. Okay, so we are told. So if you think about a 4-digit number here, that is a in the thousands column. So it's actually 1000a plus 100b plus 10c plus d. Thinking about our place value. So if we divide this by 7, well, 1000 divided by 7, what remainder do we get there? Should be 6. So divided by 7, so 1000 is equal to 142 lots of 7 plus 6. 100 is equal to, well, it's 98 is the closest to 7, isn't it? So 98 is 14 times 7 plus 2. 10 is equal to 7 plus 3. And then, well, d is just d, I guess. So this is congruent to, so when we take these modulo 7, all the multiples of 7 cancel out. So we're left with 6a plus 2b plus 3c plus d mod 7. Mod 7 just means the remainder after you divide by 7. So for example, 15 would be, I don't know, if you took it mod 4, its remainder after dividing by 4 is 3. So that's what it means. Just in case you didn't know that. So B, use properties 2, 3, and 4 to show that a plus b equals 9. So n is divisible by 9. Now, we know that if we take the sum of the digits of a number, if the original number is divisible by 9, then the sum of the digits is divisible by 9. So we know that that is congruent to 0 mod 9. It has no remainder after dividing by 9. It's a multiple of 9. And we know, what else we know? That the first 2 digits have the same sum as the second 2 digits. So c plus d is equal to a plus b. So that is equal to 2a plus b, which is congruent to 0 mod 9. So divide both sides by 2. A plus b is congruent to 0 mod 9. Or in other words, a plus b is equal to 9k. Now, these are single digits each, so you can't get as high. Well, they could both be 9, couldn't they? No, because b has to be smaller than any other digit. So the biggest a could possibly be is 8. The biggest a could possibly be is 9. You can't reach 18, so it has to be the case that they equal 9. And that's it. Okay, so C. deduce that C is congruent to that. Okay. Right. So, what do we know about... Oh, well, actually, we know... We're dealing mod 7, so we're going to have to use this. We know a plus b equals 9, so let's use that as much as possible. 4a plus 2a plus b is that part. And then there's a c plus d plus 2c. That is equal to a plus b, which is equal to 9. So that is 27. So we've got 4a plus 2c plus 27 is congruent to 3 mod 7. I suppose I never really finished that question. That's congruent to 3 mod 7 because n is congruent to 3 mod 7. Okay, 3 subtract 27 is minus 24, which is in the universe of modulo 7 equal to 4. So that means 4a plus 2c is congruent to 4 mod 7. Divide by 2, make it a bit easier. We get 2 mod 7, so c is congruent to 2 minus 2a mod 7. What do we actually want? 5. Ah, okay, well, this is the same as 2 minus 2a plus a multiple of 7, that's fine. So, and take a multiple of 7, that's fine. So that is going to be 5a minus 5, which is equal to 5a minus 1 mod 7, as required. Okay, now hence determine the number n, verifying that it is unique. You must make your reasoning clear. Well, okay, well, since b, so I think the most restrictive thing that we've got is the fact that a plus b is equal to 9. So let's do a good old-fashioned table. So if a plus b is 9 and a and b is strictly less than all the other numbers, then if these equal 9, it could be the case that it's that, it could be that, it could be that, it could be that, it could be that, it couldn't be anything else. That's all we've got. That's all we've got. And we know that C is completely determined by A, because we take A, subtract 1, times it by 5, take it mod 7, and that's C. And then we know that C plus D is equal to 9, so D is then determined by C. So by considering just these 5 options, we've got everything that we actually need here. So 5 lots of 9 minus 1 is C, but we take it modulo 7, so C is 5. And then the pair of that is 4. So I currently don't see anything wrong with what we've got there. B is less than everything else. Both of those add up to 9. Oh, C has to be even. That can't be the case, because then C is odd. So I'm making my reasoning clear. C is odd, which means that that possibility can't happen. So let's try the next one. 35, that means C is 0. That can't happen at all, because B is now not strictly less than C. Okay, let's try the next one. A is 7, so C is 30 modulo 7 is 2. Again, can't happen because B is not less than C. If A is 6, then C is now 4 and D is 5. That looks fine. B is less than everything else, adds up to 9, adds up to 9. And C is even. So this looks good. Let's, we have to show that it's unique, so we have to show that the last one doesn't work. So that is now where C is 6, and D is 3. And again, can't happen because B has to be the smallest digit and it's not less than D in this case. So 6, 3, 4, 5 is the answer. And to think that that is 12 marks, and it probably took about 5 minutes, and that last question, 8 marks, took about half an hour. And that's it from the paper.
Nice.
I told you I was going to enjoy it. So, yeah, I mean, I suppose I'm good with number theory, and I'm good with groups. So I found those questions probably easier than most. Whereas I imagine an A-level student, their integration is probably better than mine, because I don't have to do much calculus at all. I didn't have to do it in my PhD. I don't have to do it in my day job. So it's a bit rusty. So I think that's why I probably struggled on that question more than it was intended. I would be interested to see what the answer is supposed to be to that, like what the solution is meant to be, because I think I made that harder than it really needed to be.
Well, we got there in the end.
We got there in the end. Okay, so what have we got next? We've got, I think I'm going to do another A-level paper. We need to make a dent in those. So I've got 2 more A-level papers here. So let's do one of those. You know what? That further maths paper, apart from that one question, it wasn't too bad. It was, I really dreaded that. In fact, I think I did that in about, when did I start that? Less than 2 hours ago, I think. So, not too bad. Not too bad. All right, let's.
There's got to be one. There's got to be one question to separate the, the cream of the crop.
For the wheat from the chaff, as it were. I mean, yeah, it's just. I remember last year, it must have taken me about 3 hours to do one of those further maths papers. It was a nightmare. Just so messy, such ugly questions. So, how well do you remember your A-level, Creamer?
Not well at all.
Not well at all.
Let's see. But I think I've lost a lot of the techniques.
Right. Okay. Well, we'll see. So, I think I'll just power through here. Try and get these A-level papers out of the way. Okay. So, factor theorem. Right. So x plus 3 is a factor, which means f of minus 3 is equal to 0. So we've got, what we got here, minus 81 plus 18a plus 12 plus 5a is equal to 0. So we've got 81 minus 12 is equal to 23a. 81 minus 12 is 69, so 23a is 69, so a is equal to 3. Easy. Easy peasy. So, okay, looks like a nice trig graph here. Figure 1 shows a plot of part of the curve with equation y equals cos x, where x is measured in radians. Diagram 1 on the opposite page, okay, is a copy of figure 1. Use diagram 1 to show why the equation cos x minus 2x minus a half equals 0 has only one real root. Oh, I thought this was going to be a transformations question, but actually it isn't, because cos x equals 2x plus half. Now if we draw a line on here with gradient 2 and intercept of a half, so it's going to go through here. What does a gradient of 2 really look like on here? So that's pi, that's about 3, it's about 1, so for every 1 it goes along, it goes up. So it's, I don't know, it's going to look something like that. Clearly it's only got one point of intersection, so it's only got one real root. Given that the root of the equation is alpha, and that alpha is small, use the small angle approximation for cos x. Now, so basically when theta is very small, this approaches 1 minus theta squared on 2. I think. I'm going to double check that with the formula book. Fairly sure it's that. Yeah, it is that. So to find the value of alpha to 3 decimal places. So 1 minus x squared over 2, take 2x, take half, is equal to 0. So let's times the whole thing by 2. Equals 0. So that means we've got x squared plus 4x take 1. Yeah, because that becomes plus 1, so minus 1 is equal to 0. Okay, doesn't factorize obviously, so, and it wants it to 3 decimal places anyway. So x, I'm going to complete the square here. That'll do it. So x is equal to the square root of 5 minus 2. Now why is x equals minus root 5 minus 2 not a solution? Because it needs to be in the first quadrant, I guess. Solution needs to be in the first quadrant. Because, well, look at it, it's up here. It is interesting that we get another solution, though. I guess it's come from this small angle approximation. So we're bringing a squared in just because that's what the function approximates, but it's not actually what the function is. So we just have to use our common sense to choose which of those solutions to keep and which one to ignore, I suppose. Okay, this is your classic A-level question, isn't it? Where you've got some stinking great algebraic fraction. Find dy by dx. Okay, looks like it'll be a nice one where it'll simplify. So there's two sort of approaches here. You could make that a minus 2, put it up there and use the product rule. I tend to favor the quotient rule for these. Let's do that. So dy by dx is equal to x plus 1 all squared times the derivative of the top there. So 10x plus 10 minus 5x squared plus 10x times the derivative of the bottom. And it's all over the denominator squared, so to the power of 4. Alright, so first thing we notice is we've got an x plus 1 that will cancel like that. So we can do 10x plus 10. I'm not going to expand it out straight away because I'm worried I'm going to make a mistake there. Subtract 10x squared plus 20x all over x plus 1 cubed. Now it's telling me that we're just get a constant up here, so I'm quite excited to see what happens next. We should see some fireworks. So 10x squared plus 20x, good, we've got 20x there, it's going to cancel, plus 10, take 10x squared, take 20x. So, ready for some fireworks. We've got that cancelling with that, and we've got that cancelling with that. So it all boils down to, and we've got the denominator still of x plus 1 all cubed. We've got 10 over x plus 1 all cubed. A is 10, n is 3. Hence deduce the range of values for which dy by dx is less than 0. So this whole thing is negative. So dy by dx is less than 0 if and only if x plus 1 all cubed is less than 0, because you have to divide by a negative to create a negative, and that's only true if x plus 1 is less than 0. In other words, x is less than minus 1. Done. Okay, it's been alright so far. The first 3 terms in ascending powers of x of the awkward questions now. So we have got 4 minus x to the power of, I swear, did I just write 4 minus x? Or it's 4 minus x squared, wasn't it, a million times in that horrible further maths question, to the minus half. Okay, Now, let's just think carefully about this, because to apply the binomial theorem, which is 1 plus alpha to the n, 1 plus x to the alpha is how we usually do it, which is 1 plus alpha x plus alpha minus 1 to the x squared over 2 factorial, and so on. We need to get it so that this is a 1 here. So we'll pull out a 4. Some people are much better at this. This is the way I always favor to do it. So then we've got 4 to the power of minus 1/2 is 1/2. Because it's 1 over root 4. 1 minus x over 4. And sometimes I even go as far as to write that to remind me that that is going to be a minus x on 4. So we're going to substitute that where x is minus x on 4. Half the whole thing, alpha is minus 1/2. It should be fine. So 1 plus alpha minus x on 4 plus, and we need to do half of all of this, don't we? Alpha minus 1 minus x on 4 all squared, all divided by 2 factorial. And then we've got all the other terms in the order of x cubed. Okay. Just need to tidy this up now. So we've got 1 plus 2 times 4 times 2 is 16, so x on 16. Right, okay, alright, let's just do this on the calculator. Half times minus 1 on 2 times minus 3 on 2 times minus 1/4 squared, all on 2 factorial, which is 2. 3 over 256, so plus 3x squared over 256. Okay, they're the first 3 terms. The possible expansion can be used to find an approximation to root 2. Possible values of x that could be substituted into this expansion are that, and that. State, giving a reason which value of x should not be used. Right, well, this looks fishy, because this is only valued, this is only valid for 4 minus x less than 1. In other words, minus 1, 4 minus x, 1. In other words, minus 5 is less than minus x is less than minus 3. In other words, 3 is less than x is less than 5. So do not use minus 14 because it's outside of the range. Although having said that, all the other ones are outside of the range as well. What's gone on? What's gone wrong there? I wonder. Strange.
It's not the bit where you've tried to break minus x over 4 to. Should it be? So they both, if they're both, you know, the bit where you. And it's 2 minuses.
Sorry, your audio's gone really bad there.
Oh yeah. Okay.
You mean this step here?
You've taken a half out of the bracket. In order to do that, I think, haven't you times minus a half times?
Taking the half out.
Or I was just wondering if that's one of them. Oh no, wait, sorry.
Ah no. Right, yeah, your audio is really breaking up there, but I think yes. So this is valid for 1 plus, so 1 minus x on 4 less than 1. Yes. And this is going to give us a bigger range, which is good because I want to scoop up these values. So minus 1 is less than 1 minus x on 4 is less than 1. So minus 4 is less than 4 minus x is less than 4. So minus 8 is less than minus x is less than 0. So 0 is less than x is less than 8. Yes. Yeah, I couldn't quite hear you there, but I think that was that got me. That was enough. That I could do the question. So yeah, it still sounds really bad actually. Your signal, I think. So we can't choose x equals minus 4 as outside of range. State given a reason which of the three values would lead to the most accurate approximation to root 2. Now that kind of suggests that it wants me to consider these as being valid, right? But according to this, it isn't. I still feel like I'm doing something wrong here. Because this one is the only valid value of x. What does it want from me? If both of these were valid, I would go with that one. Because a smaller x will usually converge faster, I think is the idea. But why is x equals minus a half not valid? Well, if x is minus a half, then 1 minus that on 4 is 9/8. So it's not valid. So I've either done the whole thing wrong or I've done the last part. I'm gonna take my chances and just think I've done this part wrong somehow. Yeah, x equals 2 because it's valid. Let's go with that. Not entirely sure about that one. I'll be honest. Okay. Write f of x in that form. Where a, b, and c are integers to be found. Okay, so it just wants me to complete the square. That's fine. You know, that could be a GCSE question, really. X squared plus 2x plus 9. So making that, and then I've got x plus 1 all squared. Subtract 1 plus 9. So x plus 1 all squared. Take 2 plus 9 is plus 7. Sketch the curve with the equation y equals f of x, showing the any points of intersection with the coordinates and the coordinates. Okay, so little sketch here. The turning point is going to be at minus 1, 7. It's going to cut through at 9. It's got no real solutions, so that's it. Describe fully the transformation that maps the curve with equation that onto the curve with equation that. Ooh, fine. So g of x is 2 x squared take 4x plus 4 plus 4x minus 3. We're just going to expand out and then compile it all together and then complete the square again. So 2x squared minus 8x plus 4x is minus 4x. 8 minus 3 is plus 5. And now this is 2x squared minus 2x plus 5. This is 2x minus 1 squared, subtract 1 plus 5, which is 2x minus 1 squared. So minus 2 plus 5 is plus 3. So it has gone from here to here. So this is f of x minus 2, and then we've subtracted 4. So it is a translation. And what is a translation? 2 in the x direction and minus 4 in the y direction. Okay, and find the range of that function. Okay, so it's dividing by f of x. Now, the lowest the f of x could possibly be is going to be, so that f of x is greater than or equal to 7. And it could be bigger. So it means if that's the smallest that that could possibly be, that's the biggest that h could possibly be. So h of x must be less than or equal to 3. Because we're going to be dividing by bigger and bigger things. And it's never actually going to reach 0. So let's say strictly greater than 0. Okay, obviously that's where it wants me to do my sketch, but I've just done my sketch with the rest of the questions. Okay, good old-fashioned trigonometric identity. I already did an absolute monster in the first A-level paper just before. Giving your answers, solutions based entirely on graphical or numerical methods are not acceptable. Understood. So, sine, let's get rid of that double angle. That's 2 sine theta cos theta. So this is 10 sine theta cos theta is equal to 9. And let's split tan into sine theta over cos theta. The sines die. We get cos theta is equal to root 9/10. So theta is equal to shift cos root 9 divided by 10. And are we in degrees? Yes, we are. So theta is equal to 18.43. And just thinking about cos, so it wants solutions between 180. So solutions are there. So we also have minus 18.43. Cos is an even function, which means it's the same value, positive and negative. Okay, so deduce the smallest positive solution to that equation. So obviously it's going to be related to this somehow. Okay. Right, so all it's done is it's replaced theta with x minus 25, isn't it? Because then 2 theta here, that's 2x minus 50, is 2 of those. So, in other words, x minus 25 is equal to 18.43 or equal to minus 18.43. We want the smallest positive. So we're going to do x is equal to 25 minus 18.43. 25, subtract that, is 6.57. Okay. Now, I wonder, if we do 5 sine, 2 of those take 50, subtract, this is how I used to check my answers, subtract that, this should be 0. Yes. Fine. Wow, that was quite easy for quite a lot of marks. It's a modelling question. I've already had a nightmare with this today. In a simple model, the value V pounds of a car depends on its age. The following information is available for the car. Okay, when the car is new, that's when t is 0. That's when t is 1. Fine. Use an exponential model for car A to find a possible equation linking v with t. Well, in an exponential model, we have v is equal to some constant times a times some constant to the power of some constant times t. Then we use our initial conditions to work out the values of a and k. Well, when t equals 0, that's just 1, so a is equal to 20,000. So, and now 16,000 is equal to 20,000 times e to the kt. So 16,000 divided by 20,000 is the same as 4/5. That's equal to e to the power of kt. So that means, okay, a bit of logarithms here to work out this then. So log 4/5 is equal to k, because this is when k equals 1. Okay, fine. Does it want me to keep it as log of 4/5? Log of 0.8. Let's do it to a few decimal places. So that's equal to minus 0.223. So v equals 20,000 times e to the power of minus 0.223 t. Okay. The value of car A is monitored over a 10-year period. Its value after 10 years is £2,000. Evaluate the reliability of your model in light of this information. So, what does our model say that it should be? It will say something like that. So 20,000 times e to the power of minus 0.233 times 10 and 1,945. Now, how reliable is that model? Is that model when the actual answer is £2,000? I'd say it is quite reliable. Not perfect, but I mean, as models go, that's pretty good, I'd say. I don't really know how much detail it wants to be. If there's if there's like a specific way to test the reliability of a model like that, but it's quite good. Now, thank you very much, Catherine, for reminding me to update the exam counter. I absolutely knew that this would happen. So let me just do that now, because we are only on exam 10. I thought I was getting right into this. I've got to say, I feel tired. This is affecting me a lot more than it did last year. I'm feeling it. So this is.
How are you doing with the coffees and stuff? Have you had any yet?
I had a cup of tea before, but I'm trying to avoid the coffee, because apparently what happens with that is you end up crashing afterwards.
Yeah.
But, you know, if it gets to the early hours of the morning and I'm struggling, it's going to be coffee city until I finish these papers.
Yeah, okay.
What do you think about that compared to £2,000? Pretty good?
Not bad, is it?
So, explain how you would adapt the equation in... I should read the question. The following information is available for car B. It has the same value when new as car A. Its value depreciates more slowly than that of car A. Explain how you adapt equation... okay, so A equals 20,000 is the same as it was before. I promise that's what it says there, 20,000. Doesn't look like it. K, however, we need to make K... okay, so it's 20,000 over e to the power of 0.233t. So we need to make that bigger, which means we need to make k more negative. And yeah, that's a funny conceptual thing, you know. Do we consider the number -5 to be bigger than -2? We don't, because we order them like that, but we like to say that is a larger negative number than -2. You know what I mean? Like,
yeah.
that's just one of those. So I'm going to write more negative there. Yeah. I think that'll cover
You
it.
can't go wrong. Yeah.
Yeah. Okay, this looks like your typical area integration with bounds sort of fair. Usually I'm alright with these sort of things. So, figure 2 shows a sketch of part of the curve with that equation. So, a nice little cubic there. All factorized nicely for us, actually, which is good because we now know that that's -2 and that's 4 without having to do any work. Show that the exact area of R1 is 20 on 3. Okay, so we literally are just going to integrate this. We should first expand, so we get x squared, take 2x, take 8, which is x cubed, take 2x squared, take 8x. So we are doing the integral from -2 to 0 of x cubed, take 2x squared, take 8x dx, which is going to be x to the 4 on 4 minus 2x cubed on 3 minus 4x squared. Don't have to worry about the constant between 0 and -2. So this whole thing becomes minus. So -2 to the power of 4 is 16 over 4 is 4. -2 cubed is -8 times 2 is -16, so plus 16 on 3. And -2 squared is 4 times 4 is 16, so we're going to subtract 16. Okay, so 4... Let's calculate it now. 4 takes 16. Add 16 on 3. And then take the negative. That's 20 on 3. That looks familiar? Yes, that's exactly what we wanted. Alright. Can't really ask for more than that. Okay, the region R2 now. So R2, let's try and show you the question. R2 also shown is bounded by the curve. Okay, so it's just this kind of line B here, isn't it? Okay. The area of R1 is equal to the area of R2. Verify that B satisfies the equation. So in other words, 20 over 3, because it has to have the same area, is equal to the integral between 0 and B of this. Okay. Fine. Okay, so that's equal to b to the power 4 on 4 minus 2 to the b cubed over 3 minus 4b squared. And that is equal to that. So what are we actually asked to do here to show that it satisfies that equation? Okay, do we look like we're on the right lines here? Right. Something is worrying me already about this, and that is this positive 20 here. So I could factorize this to death, but when I take that over there, it's going to be minus 20 over 3. And I don't like that because all my constants are going to times to make a negative thing, which means we can't have positive positive. So something's gone wrong here. So the area of R1 is equal to the area of R2. Oh, okay. That's sneaky actually, isn't it? That is sneaky because... Okay, so the area is the positive value of the integral. So... minus 20 on 3 is equal to that because it's below the axis. You actually get a negative value when you add up all of those, but the area is the positive value. So let's go with that. Okay, if we, the question is just saying sort all this out, and you end up with what it is in the question. Okay, so let's times it through by 12. So I get minus 80 is equal to 3b to the power 4 minus 8b cubed minus 48b squared. Put that over there, equals 0. Okay, now, this is supposed to factorize nicely, is it? That's what you're telling me? So I'm going to kind of cheat here, because I know that the question is a verify that question, so I am allowed to actually use this as part of the... you know, one valid way to answer this question would be to expand all of this and then show that it's equal to that. I think that's the boring way. I am going to kind of cheat. I know that b plus 2 comes out as a factor. So I know I need a 3b cubed here. And I know I need a plus 40 here for my constant. Now this is going to give me a 6b cubed. I want minus 8b cubed. So I need to subtract 14b squared, which is going to be generated by that bit. And now for this is going to now give me a minus 28b squared. I want minus 48b squared, so I need to deduct another 20b to marry up with that. Now it's also saying another b plus 2 comes out of this. So 3b squared, there's our plus 20 that we want. Now this is going to give me a 6b squared, so I need a minus 20b to counteract that, to bring me to my minus 14b squared. And now let's check it with the linear bit. So I get minus 40b plus 20b is minus 20b, and that's what it says in the question, so we are happy. Well, happy is a strong word, isn't it? But happy enough. So...
low bar.
It is a low... okay, the roots of that equation are that and that. The value of b is therefore... Okay... Yes. So I agree we can't take b equals minus 2 because b is definitely positive when we look at our diagram. So it's saying that the two options for b turn out to be 1.225, which is clearly what it is, but you also get a b over here, which is 5.442. Now, why does that turn out to be a solution? Well, if you have b, I'll do another sketch. If you have b all the way out there, then the sum total of, you would get like that, which is negative, added to this bit of area would equal 0, and then the value of this bit would equal the value of that bit. So you still get that the areas are the same, but we know that b is there, so it's just that part. So question C diagram. I'm sure the examiner understands what I mean by that. Alright. Oh, and look, it even gives me room for a diagram. That gives me more confidence that I can just draw a diagram and that's the answer. Okay, so some logarithms now. So we've got that, so show that. Okay, well, if log A take log B is equal to log that, then that means that log A over B is equal to log A minus B. In other words, A over B is equal to A minus B. So A is equal to AB minus B squared. A1 minus B is equal to minus B squared. So B squared is equal to B minus 1A, and A is equal to B squared over B minus 1. Happy with that? Question B. Write down the full restriction on the value of B. Explain the reason for this restriction. Full restriction on the value of B. Huh. Well, this is saying B shouldn't be equal to 1. Although when that happens, we just get that log A is equal to log A. We haven't used that yet. So what is this saying? Right, so A can't be, so log A is undefined when A is less than 0. That much is certain. And we are creating negative values here because B squared is always positive, and we need B minus 1 to always be positive as well. So B must in fact be greater than 1. So 1 is less than B is less than A is the restriction there. I think that's what that's getting at. Fine. All right. So
Is that also just because if B was 1, then it would be infinite?
well, yeah, that was my first thought. And when you put B equals 1 into here, you get,
Yeah, that's what I'm looking. Yeah.
yeah. So so B equals 1. This breaks down because we're divided by 0. Why does it break down here? Well, log 1 is 0. So this equation degenerates into log A is equal to log A minus 1, which is impossible. So that's why this restriction is falling out of that. But I also think it's looking for this. And we are including the fact that B can't be 1 in that. In there. Okay,
Right.
So prove that for all natural n squared plus 2 is not divisible by 4. Okay, nice. So I thought this used to be, well, in fact, let me just think about this. So I'm thinking that I thought that this was a proof by induction question. But maybe it isn't. Maybe you can do it algebraically. No, let's do it by induction. So induction, do you know about this? Because it's one of my favorite principles in.
No.
So if you, it's such an amazing, like the fact that this was figured out. It's such a gloriously simple yet powerful tool. So if you have a statement like this, how can I explain this? What's a good example to use here? So it's basically, if you have a statement that you make about any of the natural numbers, so these are the numbers from 1, 2, 3, just the integers are positive. If you know that the statement is true when n equals 1, and then you know that if the statement is true for n equals some random k, then it's true for the next k, then you've therefore proven that it's true for every integer. So basically what you're doing is, if it's true for this, then it's true for the next one. Well, that means that if we already know it's true for 1, we've then proven that it's true for 2, because we've said if it's true for a general k, then it's true for the next k. You know what I mean? So if it's true for some random integer, then it's true for the next random integer. And if we show that it's true for n equals 1, then it must be true for n equals 2. And if it's true for n equals 2, it must be true for n equals 3. And therefore, it must be true for all of the integers, which it's just amazing. Okay, so n equals 1. Sometimes call this the base case. So it's the base of our induction. So n squared plus 2 in this case is 3, which does not divide. Sorry, which is not divisible by 4 because it's 3. Okay, so assume k in n and k squared plus 2 is not divisible by 4. Then let's see what happens with k plus 1. So with k plus 1 squared plus 2, that's equal to k squared plus 2k plus 1 plus 2. that's equal to k squared plus 2 plus 2k plus 1. Now, we've already assumed that that is not divisible by 4, and this here is an odd number, because whatever integer this is, 2 times that integer is even, and if you add 1 to it, you get an odd number. So that's also not divisible by 4. So the result holds for all n in n. Okay, given a real number x, the value of that is greater than or equal to the value of x minus 9. State, giving a reason, if the above statement is always true, sometimes true, never true. Well, it's definitely true sometimes, because if I choose x equals 0, then I get mod 28 and I get minus 9, and mod 28 is 28, which is certainly greater than that. So it's definitely, that's out. Is it always true, or is it only sometimes true? I think this is going to be sometimes true. Let's just see if we can find a nice counterexample. So what do we actually want? We want this to be really small. So as close to 0 as we can get. Let's choose x equals, I don't know, 10. Then 3x, so that's 30 take, so that will give me 2, whereas 10 take 9 is 1. That's even that greater. What is 28 divided by 3? Because there's no reason why we can't use that, right? So, so 3 times 28 on 3 minus 28 equals 0. Whereas 28 on 3 subtract 9 is equal to a third. So 0 is not greater than a third. So it is only sometimes true, because I found a case for which it is true, and I found a case for which it is false, so it cannot be always true, so it is sometimes true. Always try to find counterexamples first, because if you find one counterexample, you're done. If you have to prove that it's always true, then you have to give a proof. So counterexample is usually the way to go. Okay, a competitor is running a 20-kilometer race. Good for you. After she runs the first kilometers at a steady pace of 6 minutes per kilometer, after the first 4 kilometers, she begins to slow down. In order to estimate her finishing time, the time that she will take to complete each subsequent kilometer is modeled to be 5% greater than the time that she took to complete the previous kilometer. Right. Okay. Using the model, show that her time to run the first 6 kilometers. Okay, so she runs the first 4 kilometers at 6 minutes per kilometer. So that takes 24 minutes. So that's kilometer 3 is at 6 kilometer. So kilometer 5 will be 1.05 times 6. And kilometer 6 will be 1.05 squared times 6. So 24 plus 6 times 1.05 plus 6 times 1.05 squared is 36.915. Okay, so added together is 36.915. Okay, so that's 36 minutes. And this decimal here, that is 0.915 of an hour. So of 60 minutes is 54.9 minutes, or 55 minutes. as required. Okay, B, show that her estimated time in minutes to run the rth kilometer is that. Oh. Well, it's kind of what I did there. So what does it want? Okay, yeah, I mean, that's what it is, you know. It's 6 times 1.05 to the power n, where n is after the first 4 kms. So this is 6.1.05 to the r minus 4, because that starts at n equals 5. Well, no, it starts at n equals 5. It starts, so n equals 1 at 5. So 5 minus 4 gives us the value of n, or what we're calling r here. I mean, I don't know. That's a weird question. I don't really know what it's asking me there, because that's just that is what it is. Estimate the total time in minutes and seconds she will take to complete the race. Ooh, this is a geometric progression. So A is 6 times 1.05. R is 1.05. Sum of a geometric progression. Now n in this case is we're adding up 16 terms here. So have I done that correctly? Yeah. 16 terms, starting from there. Okay, so, oh geez, what is it? What is it now? A 1 minus r to the n over 1 minus r, I want to say. I'm going to check the formula book on that. So, yeah, that's right. That's fine. So A 1.
When was the last time you used that equation?
Oh, I don't even know. Played this time last year, actually.
That's fair.
And that's 6 times 1.05, isn't it? So I actually know the proof of this, so I kind of replay the steps of the proof. Well, I vaguely know it, and I think because I vaguely know it, you can kind of feel out what it is. 6 times 1.05 times 1 minus 1.05 to the power of 16 over 1 minus 1.05 is equal to 149.04. But let's not forget, she needs to run those first 4 kilometers at 24 minutes. So add 24. So it's 173. So in minutes and seconds, that is 173 minutes. That's close to 3 hours, actually. And then times 60 and 3 seconds. Is that right to run 3 kilometers? Yeah, 20 kilometers is quite far, isn't it?
It's a half marathon nearly, right?
Yes, that's quite slow, isn't it? Some of our mates recently ran a marathon for the first time, and they did it in about 4 hours and 4.5 hours. So this is quite slow, I would say. This competitor will not be competing very competitively.
It's a 3-leg race. It's a 3-leg race.
Oh, is it? Yeah, it's like a 20 kilometers. 20 kilometer egg and spoon race.
Yeah, exactly. I always quite like those questions where it like had a bearing on reality. Always like found those more like engaging, right?
Oh,
Wait,
not at all.
No, you just rather the pure maths with
Yeah,
no with
pure
no.
100%. Come on, you know me. I mean, we had a
Yeah.
question. We had a question before, and it was about a scientist studies slow growing trees.
Nothing will get the kids more excited.
Yeah, well, that's exactly what I said. Like, you might as well write the question of like the scientist is watching paint dry. You know.
Yeah. Some of the topics are just incredible.
And the answer turned out to be to reach a height of 12 meters. It took 63 years. And I was like, well, I don't think that's realistic because who's funding that experiment, you know?
Yeah, that's it exactly.
As someone in the biz, you know, would you get funding for that?
Yeah, absolutely not.
So, okay. So it looks like we've got a bit of differentiation here. Was probably what is going to go on. Show that the x-coordinates of the turning points of the curve satisfy that equation. Okay, so let's differentiate. Products rule. So f dash of x is equal to 10 e to the minus 0.25 x cos x plus sine x 10 times minus 0.25 e to the minus 0.25 x, and that is equal to 0 at the turning points. So we just have to show that that is somehow equal to equivalent to tan x equals 4. So I'm expecting a boatload of cancellation here. Well, the e bits cancel, don't they? And then we can divide through by 10, and then we can times through by 4, and then we can take that minus out there. So what we're left with, 4 cos x minus, well, equals sine x, really, isn't it? Oh, and that's perfect, because now 4 is equal to sine x over cos x is tan x. So a bit of cheating with all my crossings out there, but it's fine. Okay, sketch the graph of h against t, where h of t is equal to that. I'm going to look to see if they've given me... Oh, look at that. Nice plain diagram there. So what I'm going to do here, I'm going to see if I can trace that out. So it's that. Okay, and we're taking the absolute value of this, so it's going to look something like that, a bit like a ball bouncing up and down, this kind of, you know, if you throw a ball in the air. Okay, so the function h of t is used to model the height in meters of a ball above the ground t seconds after it is being kicked. Perfect. Using this model, find the maximum height of the ball above the ground between the first and second bounce. So we're looking for that point there. Now we know that tan x equals 4. Is where the turning points are, right? Is that what we worked it out to be? Yes, tan x equals 4. So x equals, what's my calculator? So inverse tan of 4, 75.96, and now we just need to stick that into the equation. So we've got 10 e to the minus 0.25 times that value of x sine that value of x. So into the calculator, 10 e to the power of minus 0.25 times that times sine of that. Oof. Now that seems very, very low to me. So what has gone wrong here? I knew this was going to happen at some point. My calculator is in degrees. But we're doing some calculus here, which means we need to be working in radians. So big boy units, 1.33. So same again, e to the minus 0.25 ans times sine ans. And that's a bit more like it. So that's 6.96 meters. Explain why this model should not be used to predict the time of each bounce. Right. I guess, I mean, if you carried this on, it would just keep bouncing and keep bouncing and keep bouncing. Well, it'd look more like that, wouldn't it? You know, still spread out. So the ball would never stop. I don't like that answer actually, because it's not really asking about that. It's asking at the time of each bounce. I suppose because it's a periodic trig thing, according to the model, the bounce is, or the time is always the same. According to the model, the time between bounces is always the same. Why is that a problem? Well, if you actually drop a ball, it doesn't go bang, bang, boing, 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 boing. It goes like boing, 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 boing. So it speeds up. Is always the same. So in reality, would speed up. That'll do. That'll do. Is that enough real world context for you there, Creamer?
Yeah, love it.
Love it. Okay, reaching the end of this one. So, a curve with that equation. Again, big stinky algebraic fraction, classic A level, where P and Q are constants, passes through that point. It has two vertical asymptotes. Okay, interesting. With equations x equal 2 and x equals -3. So that must mean that Q is 4, because, 4 minus 2. Explain why you can deduce that Q is 4. Okay, so asymptote at 2x minus Q equals 0. Therefore, Q is equal to 2. Lots of 2 equals 4. Show that P is 15. Okay, so we know that we've got this point that it passes through. So we know that 1/2 is equal to P minus 9 over, 6 minus 4 is 2. And 3 plus 3 is 6. So 1/2 is equal to P minus 9 over 12. So P minus 9 equals 6. So 6 is equal to P minus 9. So therefore P is equal to 15 as required. Okay. Oof, big 8-mark question. This is going to be some integration, isn't it? Look at that shaded region begging to be integrated. Show that the exact value of the area of R is A log 2 plus B log 3, where A and B are rational constants to be found. Okay then. Fine. That's absolutely fine. It does mean we're probably, we need a few bits and pieces before we jump in with that, don't we? So we actually need to know what that point is there. So, so this is when y is equal to 0, it's going to strike the x-axis. So if all of that is equal to 0, then p minus 3x is equal to 0, which means 3x is equal to p, which is 15, which means x is equal to 5. So we're going to be integrating between 3 and 5. Right. So the answer to the question is to integrate between 3 and 5 y dx. Okay. Now, we're going to need some machinery to deal with this stinker here. So 15 minus 3x over 2x minus 4x plus 3. I think it wants me to use partial fractions here. I don't see any other way of doing it. We could expand. Say it again.
Just coughing.
Oh, I just got. Oh, sorry. It's gonna want me to. We could expand out the bottom, differentiate, and then squeeze it into a log of a quadratic, which I think we could then factorize and do that way. I think the partial fractions are probably neater than that actually. So let's go ahead and do that. So we've got the classic partial fractions set up here, plus b over x plus 3. These are always quite fun, aren't they? 15 minus 3x is equal to a, x plus 3 plus b, 2x minus 4. So how much have we got of x? We've got 3 is equal to a plus 2b. And how much constant stuff have we got? We've got 15 is equal to 3a minus 4b. So let's times... What should we do? Let's times the top one by 2. So we get minus 6 is equal to 2a plus 4b. Add them together. Now we get 9. Ooh, 9 is equal to 5a. Really? 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 I don't like that. That's not what I wanted from this at all. I wanted it to be nicer than that. Fine. Fine, we'll play it your way. We'll do 5/9. Annoying. So that means that b is equal to minus 3 subtract 5/9 divided by 2. So b is equal to minus 16/9. Awkward. I expected not this. But I don't see where I've messed up. So minus 3 is equal to a plus 2b. I completely agree with that. And we have got 15 is equal to 3a minus 4b. Times that by 2, add them together, and we get this rubbish. Oh, I mean, horrendous mistake there. 9/5. Well, at least we're dividing by 5, which is a bit cleaner, isn't it? So, fine. So b, let's work out b again. Minus 3 subtract 9/5. How did I do that? And then divide by 2. So it's minus 12/5. Okay. Can live with that. Can live with that. It's not as nice as I would like. So the integral of y dx becomes 9/5 times the integral of 3/5 of 1 over 2x minus 4 dx plus minus 12/5 times the integral between 3 and 5 of 1 over x plus 3 dx. Now this one's fine in and of itself, but what we actually want here is a 2. So I'm going to times the top by 2, divide and divide by 2. So this is 9/10 now. So this is 9/10 log 2x minus 4 between 5 and 3 minus 12/5 log x plus 3 between 5 and 3. Hopefully this works out. I mean, what does it actually want from us here? Where a and b are rational constants. So that's a clue that they're going to be some fractions in the end. Okay, so this is log where x is 5, 6, minus where x is 3, that's 6 take 4, log 2, subtract 12/5 of, so we've got log 8, take log 6. Fine. Okay, so let's just expand it all out. 9/10 log 6 take 9/10 log 2 take 12/5 log 8. But I'm going to rewrite that as 2 cubed. You'll find out why in just a moment. And then log 6 minus times minus. Okay, so how much log 6 have we got? Do we want log 6? We want log 3. Ooh. Okay. Does it really want us to do that? I thought the log 6s would cancel, but actually what it wants us to do is to do every log 6 is log 2 plus log 3. So, alright. So, minus 9 tenths. Take 3 of those, because when you log of 2 to the power 3 is 3 log 2. That's why I made that as 2 to the power 3. So minus 36 over 5. So I've got minus 81 tenths of log 2. And now I've still got to sort out this. So 9 tenths of log 2 plus log 3 plus 12 fifths of log 2 plus log 3. This question will not end. So, how much log 3 have I got? I've got 9 tenths plus 12 fifths. So, 33 on 10 log 3. And I've got that amount of log 2 subtract 81 on 10. So, minus 24 fifths log 2. And they are our rational constants to be found. Could very well be some mistakes in there, I'm not going to lie. But I'm happy enough with that as an answer. I think it's most of the way there, bar modulo some arithmetic errors. So, any of it coming back to you?
Not really. No, it's amazing how much I've forgotten.
Right. Okay. I suppose it's been quite a while, isn't it? If you're not like,
And I just have,
go on.
yeah, I just haven't used any of it practically, really, in my job. We just don't do it at all.
Yeah.
And if it is done, it's done in the background. I don't know about it.
Yeah, so I think it was my my brother actually, who's also a chemist. He showed me the software that he uses on his NMR. Is it NMR?
Yeah.
Like the
Fourier transform.
Yeah, exactly. So it's Fourier transform, and there is like there's basically like an integral function, and you just click the 2 points between the curve to integrate it, find the area between it, and that shows you something like the likelihood of a certain thing and stuff like that. So
yeah,
it is all there. I mean, that on a computer like that, it'll be using numerical methods anyway to approximate it. You know, it won't actually be doing like hard integration. But
no,
yeah,
you're saying.
I suppose if you don't do it, it's easy to forget stuff, isn't it?
Yeah, but I mean, all this stuff is fundamental. Like we're saying, to the NMR, the raw NMR signal you get is a looks like a complete mess, and then you do magical Fourier transform, and it comes out with a beautiful graph. It clearly comes out of it. It's just kind of amazing that's.
Yeah,
you know, that's reality.
Yeah. I mean, the fact that Fourier transforms are like an extraordinary piece of maths, very very technical and like very fiddly, but they are pretty extraordinary. Just the fact that you can represent anything in terms of your your sines and causes and things, and it all turns out nicely. Have you seen the? Because I never quite got that. I saw those diagrams where it was like, you start with your cos and then you refine it a little bit so it now looks like this sort of thing, and then you refine it and it comes out to be anything. So that sort of thing. You can create like a sawtooth pattern, or you can create like a kind of a graph that looks like this. If you do it to infinity. Have you seen?
Yeah, I remember a JavaScript, like some sort of website where you could basically generate anything you wanted, and I think it was a way of illustrating the Fourier transform process. So I do remember something like that to get us into. I think that's probably first year at uni.
Right. Yeah.
To show us what's actually going on, because you need to be able to visualize it, sort of understand like why you're doing it.
Yeah. You don't need to be able to do any of the nuts and bolts of it.
No, exactly.
Yeah, that sounds about right. So some poor mathematician who's had to work all that out.
Yeah, and gets no credit for it.
Well, Fourier gets a bit of credit. We're still using
Yeah,
his name.
he gets a little bit of credit.
Yeah. Okay, should we bring this paper home? We have got a curve as defined by that. Oh, just one thing about this. Something I was going to say. I think it's a 3 blue 1 brown video where he does these Fourier series, and he does it like, and the animation is like circles attached to circles attached to circles. So as they wind around, they kind of trace out these like amazing shapes, and the more circles you want, the more refined it becomes. It's
yes, I have seen that.
really nice.
Yeah.
So we've got 1 is equal to 8 cos 2y dy by dx. So that is that implies dy by dx is equal to 1 over cos 2y, which is equal to, well, at the origin. Sorry, I've lost that 8, haven't I? At the origin where y is 0, this becomes 1, so that's an 8th at the origin. Fine. Use the small angle approximation for sine 2y to find an equation linking x and y for points close to the origin. So when theta is very small, sine theta is approximately just theta. So, you know, if you take something like sine 0.01, for example, you're going to get pretty much 0.01 back, so it's approximate. So that means sine 2y for small values of y is going to be 2y. So that means x is equal to 8y is the equation linking x and y. Explain the relationship between answers A, that one, and that one there. Ooh. Okay. Okay, so we are saying then y equals 1/8 of x, and dy by dx there is equal to 1/8, which is what we got there. Suppose that's what it wants. Okay, and last question of the paper. Show that for all points x, y lying on C, dy by dx is equal to that. Okay, so this, I think it now wants me to redifferentiate this, but in terms of sine inverse. So let's rearrange in terms of y. So x over 4 sine inverse of that over 2 is y, isn't it? So that's half sine inverse x over 4. Let's just write it like that. It's a little bit neater. Is that right? Divide by 4. Yep. So now to then differentiate this. Now I do know this. The integral of 1 over root 1 minus x squared is equal to sine inverse of x. Is it positive 1 or is it negative 1? Yes, I think that's right. And I also think... So that means obviously what we call the fundamental theorem of calculus. So we go the other way. If you differentiate this, you end up with that. So let's differentiate it. We get dy by dx is equal to a half of 1 over root 1 minus x over 4 squared. Okay, and then it just wants me to sort that out. So that's equal to 1 half. So that's x squared on 16. And 1 minus x squared on 16 is 16 over 16. So that's going to be root 16 minus x squared over 4 all under 1. So it becomes 2 over 16 minus x squared. And that's not what they've got written down there. No, I do remember that. You know what? I actually think that sine inverse of x over a becomes 1 over root a squared minus x squared. I think that's the trick here. I think that's it. I'm gonna go with that. So it's half. Let's do it again. 1 over root 16 minus. I think that's actually just it. And then we get 1 over 2 root 16 minus x squared, which looks more like what they've got here. So where a is 2 and b is 16. Yeah, I think ignore that. That was I do remember this when I did further maths, because this is the trap that I used to fall into. I like to get everything in terms of x and think of it that way, whereas I think with this it doesn't quite work out. I do have vague recollections of that. I remember having to just memorize this because that part is not in the formula book. But I think it's right. Okay.
Well done.
So we're getting that's 10. Oh, is that only 10?
No, oh yeah, okay, yeah.
I think I might have forgot to change that counter. I'm going to count how many I've done here.
Right.
Okay.
Yeah. How many? Yeah. Okay. Oh yeah. You got. Well, while you're doing that, you got some messages.
Okay.
Christopher Mort says, "Best of luck, Alex. We're all rooting for you. You'll smash it."
All right, that's really sweet. Thank you very much.
And then a guy here called Alexander Villas says, "I just want to tell you, good luck. We're all counting on you."
All right. It's funny because I've never actually heard that comment before, so
No.
no idea where it's from or what it pertains. You know, it's really funny. No, thanks very much, brothers. Appreciate that.
And Amy Williamson was watching you as well.
Excellent.
Before, I think she's still watching.
Thought she might.
Yeah, you've still got 6 people watching, and it's 10 to midnight. So
yeah, that's pretty good. Or they've just left it on in the background and they've fallen asleep. Wouldn't be surprised. So that's 4. That's 5. That's 6, 7, 8, 9, 10. Oh my god. I've made a hash of this. I'm halfway through and I've already done 10 papers.
Really ruined the build up to the halfway point.
Yeah. Is that really it? 3, 4, 5, 6, 7, 8, 9, 10. Holy moly. It feels like I've done about 80. So that means so 10. Okay, yeah, that means I need to get on with this. So I'm gonna be back in just a second.
Yeah, okay. I got confused then. Did he say that? Did he count 12 or did he count 10? Did anyone else follow that? We'll find out. Oh, okay, thanks, Brenton. I thought you said it's halfway at some point, and then I think then he counted 10 again. Maybe he said he's not even halfway. But I think he put some more difficult exams purposefully around this time so they could play catch up later. Yeah, okay. Thanks, Nestor. Yeah, it does seem to be a bit harder than last year. Probably just because he mentally knows what he knows what's coming. He knows what to expect, whereas first time probably had the novelty factor. It's lucky he bloody loves maths.
Okay, and I'm back.
Hello.
You alright?
Yeah, all good. Yeah, so just to clarify then, your counter is correct. It was just when you did the recount.
Yeah.
So
Just to rub salt in the wound, Creeper. Yeah. Just to clarify, you are doing pretty
well,
poorly.
I got confused because I swear you counted to 12 or something. I was like, what's going on?
I
Anyway.
thought I knew I was behind. I thought that was the 11th one. You know.
Yeah,
But it's
okay.
actually the 10th one. So what I'm going to do, I'm going to do this last A-level paper because looking at the pile I've got over there. So what I've got left after this is basically 6 of the GCSE level ones and 6 of the old A-level ones. So the old A-level, back when we did it, the A-level, when it was a lot easier, I might add, when it was modular, you got all the resets and things like that.
Yeah.
So yeah, they are considerably easier and shorter. These are always like 13, 14 questions, whereas in the old, you'd get like 10 questions maybe. And just generally, just a bit easier, I think. So
Yeah. So how long are you actually given for this exam you're about to do then?
you're given 2
2
hours.
hours.
Yeah.
Okay.
I ended up the total amount of time that you. So if you add up all of the times on all of the rubrics on these papers, it adds up to about 37 hours.
Oh, okay.
That's the total time that you're given. So I'm basically trying to do that in, you know, a 2/3 of the time. Which you know is fine because, you know, I don't need half an hour or an hour to do a Key Stage 2 paper. I do need the full time for the further. I mean, the degree paper, you get 3 hours to do that, and it doesn't take 3 hours. You know, once you're pretty good. Although I think I did take 3 hours doing it today because I just really wanted to talk about it. So I think that's cost me actually just prattling on and about all of the degree level stuff. But it's interesting, and I just know a lot of people last year were just like, I'm so lost, I have no idea what was going on. So I just wanted to kind of explore that.
Yeah. Well, you got to, you know, you might as well take a bit of time at certain sections.
Yeah. I mean, any maths is worth talking about, in my opinion. You know.
Of course, I would never question that.
Question.
Yeah, your dad said he's in the bar, he's playing pool and setting up a new projector.
Nice.
You're doing well.
Nice. I mean,
I'm really just picturing like a full. I know it's different times, but I'm picturing like a full bar with like you do a maths exam on the background, everyone cheering.
Yeah, like it's the Football World Cup or something.
Yeah.
I mean, you're not far off actually. So my dad has a proper like man cave set up in his basement where it's like a bar with a pool table and this projector he's obviously setting up a little cinema down there. Very jealous of it, to be honest. It looks
That's great.
Looks amazing. Can't wait to get to that age where you just don't give a crap anymore. You can just do stuff like that. You know, it's great.
All right, cool. I'll leave you to it.
So this is the last chunky paper that I've got is what I was trying to say. But once again, taking about 5 minutes, what should be said in about 30 seconds. You know, as I like to do. As teachers, we say that we should use economy of language, you know, and here I am again, just talking. Amazing. Okay, so here we have some more binomial expansion, and I thought I'd had my fill of that actually, but maybe not. At least this time, this is our usual. Oh God, what's the first 4 terms? So this gets sticky, doesn't it? So it's 1 plus half 8x plus half minus half 8x squared over 2 factorial plus half minus half minus 3 halves 8x cubed over 3 factorial. And you know what? I think my pen is struggling again. Oh my God. I can't believe I filled this up earlier today. I'm going to have to refill. Hold on. Honestly, I usually refill this pen about once a month.
We need some like lift music in the background when you go away.
Yeah, no, yeah. Get some of the Jean-Michel Jarre.
Yeah.
Which my dad is also an absolutely massive fan of. I think he would appreciate that. Yeah. And then
I don't know if he'd like the fact it's been compared to lift music, but
no, probably not. No. Jean-Michel Jarre is an experience, you know.
Yeah.
But yeah, he's been to see them live at, you know, some of those like outrageously huge concerts that he's done with like millions of people. Pretty.
Yeah, doesn't he have the record? I don't know.
Yeah, he set and subsequently broke the record. Like I think he has the record. It's like 3.5 million people or something. His Moscow one, which is just absolutely mental. But he was at the Paris La Défense one, which was like I think that was about 1 million. Just imagine trying to orchestrate a gig for 1 million people. It just doesn't make sense. Right. So I'm just going
Here we go.
calculating my way through this. So 1 plus 4x plus, well, 2 times 2 is 4. 8 on 4 is 2 divided by 2. Surely can't just be 1. I said I was going to calculate it my way through it. That's half times 8. 8 squared. That's where the thing is. So divided by 2, we get 8x squared. And finally, let's do these decimals actually. So 0.5 times minus 0.5 times minus 1.5 times 8 to the power of 3 over 6, that's 3 factorial, plus 32x to the power of 3, and so on. Okay, question B. Explain how you would use x equals 1 over 32 in the expansion to find approximation for root 5. Well, 1 plus 8 on 32 is 40 on 32. So 1 plus 8 on 32 to the power of a half is equal to root 40 on 32, which is the same as 5 on 4. Yes, root 5 on 2. So you would use that. So this is actually how these approximations are done, where you substitute x equals 1 over 32 into this, times it by 2, and it'll give you an approximation for root 5. That kind of thing is done to find approximations of pi and things like that. Okay, by taking logarithms of both sides, solve that equation. So, okay, 3p minus 1 times log 4 is equal to 210 log 5. Really? Yeah, okay. 3p is equal to 210 log 5 over log 4 plus 1, and then divide the whole thing by 3. That will give us p. So into the calculator we go. 210 log 5 over log 4 plus 1 over 3, which is 81.6 to 1 decimal place. Okay. If only they were all as easy as that. Okay, some vectors now. Point A has that position vector, point B has that position vector, point C has that position vector. Find AB. So AB. So to get from A to B, it is I minus 8j plus 2k. Or as I would always prefer to write it like that, because I like linear algebra like that. Show that the quadrilateral OABC is a trapezium. Ooh. That question has a bit of heft. So okay, OA is, I'm going to do them as column vectors, it's so much easier. 2, 5, minus 6. AB is 1 minus 8, 2. We need BC. We don't have that yet. So to get from B to C, it's going to be minus 1 minus 13. 8, and then from C back to O will be OC but negated, so minus 2, 16, minus 4. Now, what I want is for one of these, either these two or these two to be parallel. Yes, AB is equal to, sorry, minus 2 of AB is equal to CO. So, parallel. And OA not parallel to BC. Why is it not? Well, because if I, for example, wanted to times these numbers by something to make those numbers, I would have to times it by minus 2. I'd have to times minus 1 by minus 2 to get 2. But that doesn't make the other numbers work. So it must be a trapezium because you've got 2 parallels, 2 not parallels. So you must be looking at a trapezium. Now, kind of lurking in the background of this question is the fact that, is this a planar object? Because there's no reason if you're in 3 dimensions that this has to be a planar thing, because you could have something that goes like up like that and then across and then, you know, kind of skewed like that. So if you've got your 4 vectors, they could be kind of warped in such a way that it's not a quadrilateral. But I'm just going to assume that we can it says quadrilateral OABC, so I'm going to assume that that's fine. But that is a feature of the question that isn't entirely obvious to me. I suppose if you know that these are parallel, then the only way, then maybe it does force it into a plane. So it is a quadrilateral. I don't know. We'll answer that question the same way that writers of textbooks like to answer it, and that is exercise left to student. Now I've already had one of these. So F inverse of 7 it wants me to find. But what I'm going to do is there a quick way of doing this? So this is equal to something, and that means that F of F inverse of 7 is equal to F of A. So 7 is equal to F of A. So I want to find the value of A. So let's do 3A minus 7 is equal to 7A minus 14. So 4A is equal to 7A is equal to 7 quarters. Let's check that, actually. Because that's a funky answer to end up with at the end. Minus 7 over and minus 2. 7. Yeah, fine. B, show that FF of x is equal to that. So we need to do 3 of 3x minus 7 over x minus 2 minus 7 over 3x minus 7 over x minus 2 minus 2. Oof. Okay then, if you say so. So x minus 2 over x minus 2, x minus 2 over x minus 2. So this is all going to boil down to 9x minus 21 subtract 7x plus 14 over x minus 2 over 3x minus 2x. Well, let's just write it. 3x minus 7 subtract 2x plus 4 over x minus 2. And let's bracket the hell out of that because that is confusing as anything. So imagine you're going to flip that upside down and cancel it. You get cancellation. 9x minus 2x is minus 7x is 2x. Minus 14 plus, that's minus 7 over x minus 3. And that is in the form that we want, so I'm happy with that. Nothing like a bit of algebra. Okay, so a car has 6 forward gears. The fastest speed of the car, well, here we go with some real world application. The fastest speed there is that. Given that the fastest speed of the car in successive gears is modeled by an arithmetic sequence, right? So first term 28, sixth term is 115. This is the kind of question that I ask my year 7s, you know? Because you're basically doing stuff like this. So you need to add on 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So if we need to add on D, we've added on 5d to 28 to get to 115. So if we do 115 subtract 28 and then divide the whole thing by 5, and that's equal to 17.4. That's our common difference. Now, what does that mean for the third gear? Well, it's 28 plus that, and that gives us 62.8. Yeah. So B then. I mean, there's no way a car would actually progress in an arithmetic sequence like this. Usually, I think gear ratios are usually more, not exponential, but you know, I don't know. Oh, okay. Now it's modeling it by a geometric sequence. So 28. If we multiply it by the common ratio r, we get to the next term. 2, 3, 4, 5. So r to the power 5 is equal to 115. So r is equal to the fifth root of 115 on 28, which is shift root 5, 115 on 28. So that is our common ratio, 1.32. So then we need to get to the fifth gear, 28r to the power of 4. So 28 times that to the power of 4, and we get 86. And that seems more realistic as a gear shift sort of thing. So the maximum speed you can get, kind of, you know, the difference between them increases and increases, you know. That feels more. I mean, you drive an automatic these days, don't you? So, you know.
Yeah, again, it does all for me.
Yeah. Yeah, your approach to cars is the same as your approach to NMR spectra.
That's exactly it.
You want a mathematician in a closet somewhere who's going to do all the math for you. Okay, express sine x plus 2 cos x in the form Ri. Now, I'm actually glad that it's given me this, because I'm really bad at spotting when to do this this trick here. Because when I would go ahead and try and solve this, I'd go brute force, usual sort of way, but this is a nice little trick to do it. Okay, so all right, double angle for sine is oh god, it's sine x cos alpha plus cos x sine alpha. And we are saying that this is equal to sine x plus 2 cos x. So the amount of cos x that we've got is 2 on this side, and the amount of cos x that we've got on that side is r sine alpha. And the amount of sine x we've got on that side is 1. The amount of sine x we've got on this side is r cos alpha. So that implies that tan alpha is equal to 2. So alpha equals shift tan. Now, we check it just radians now. So I'm in radians. So shift tan of 2. Alpha is the value of radians in 3 decimal places, so 1.107. Now, sine of that is that. So 2 divided by that will give us r. Oh, but it wants the exact value of r. That's interesting. Shift tan of 2. How are we going to get our hands on that then? Somehow need to eliminate the exact value of r. Okay. 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 I don't know if I'm reading too much into this question. It's the fact that it says give the exact value of r. So I can shove that in there and solve for r no problem, but it's not the exact value. And I just get the feeling that it doesn't. It's not. Okay, what about this? What about if we do r squared sine squared alpha is equal to 4 and r squared cos squared alpha is equal to 1, and then we add them together so we get r squared sine squared alpha plus cos squared alpha is equal to 5, and that is 1. So now r squared is 5 and r is root 5. Okay, that'll do. So let's check to see if that holds water. So shift tan of 2, that's our value for alpha. If we take the sine of that, we get that, and 2 divided by that is our value for r. Now what is root 5? It is 2.236 blah blah blah. Yes, it's exactly the same. So that is absolutely correct. But the calculator wasn't clever enough to pick out that that was root 5. All right, that was an interesting little part of the question. I didn't quite, couldn't see what to do for a second there. Okay, the temperature theta degrees inside a room on a given day is modeled by that equation. Okay, so it's modeled by, it's this, isn't it? But with x is equal to pi t on 12 minus 3. Okay, so x is equal to pi t on 12 minus 3. And we've added 5 to this. Use the equation of your model in your answer part A. Deduce the maximum temperature of the room during this day. Well, actually, we don't need to substitute anything into here, I don't think. But let's just right. So let's just a recap of where we got to. We got that sine x plus 2 cos x is equal to root 5 sine x plus 1.107. So that's where we got to with that. Now it's given us this temperature of room thing.
Catherine's put a couple of things in the chat.
Oh yeah. And that's what I ended up doing. Yeah. So yeah, I think I should have noticed, because the whole point is we wanted to eliminate the alphas, and the only way to really do that is with some kind of identity. So squaring and adding them, that was the way to go. So in this one, we have that theta is equal to 5 plus all of this. And all of this is equal to that, where x is, so 5 plus root 5 sine pi t over 12 minus 3 plus 1.107. Okay, and that's fine. But we, regardless of what t is, we take the sine of it, and the absolute biggest that sine of something can be is 1. Imagine your graph, no matter what you do with that, you're taking the sine of something, that's 1. So the theta is maximized at 5 plus root 5, which is about 7.24. Okay, find the time of day when the maximum temperature occurs. Giving your answer to the nearest minute. Well, we want sine of all of that gubbins to be equal to 1. Now that occurs at when this is equal to pi, right? Not making a fool out of myself here. Sorry, pi over 2. Yeah, half pi. So in other words, pi t over 12 minus 3 plus 1.107 is equal to half of pi. Alright, so I think we just need to sort that out. So minus 3 plus 1.107 first of all. Add that to pi by 2, times it by 12, divide it by pi. Oh dear. Oh dear. So maybe maybe that's not right, because we could have pi, or we could have 3 pi by 2 here actually, so maybe that's what it wants me to do, but that doesn't make sense. That doesn't make sense. Let's try again. I actually think we should go with this. I think I've just made a mistake in the arithmetic there. So pi by 2 plus 3. I think that's what I did. I think I added on that when I should have subtracted. Subtract that, times it by 12, divide it by pi, and we get t is equal to 13.23. Okay. That seems... Okay, and that's t hours actually, isn't it? So it wants 13 by 60. Okay, well, it's at 13 hours, let's say, and so take 13 times by 60, and 14 minutes. So is it after midnight? Yeah, so it happens at 13:14. And maximum temperature occurring at 13:14 is reasonable, I would say. You know, usually the maximum temperature is sometime in the afternoon. Okay, looks like our standard compound area style question. So figure 1 shows a sketch of a curve with that equation and some kind of straight line. The curve C meets L at those points. The shaded region R is bounded by C and L. F of x is a quadratic function with that turning point. Right. Use inequalities to define R. Alright, well first I think we can get our hands on C, can't we? Because we know the minimum. So we know the minimum looks like that. But it could be a scaled parabola, so we need a parameter like a in there, squared. So let's put it in that form for now. And what else do we know? Well, we know that its y-intercept is 25. Okay, so if I expand this out, x squared plus 4x plus 4 plus 13, then that means ax squared plus 4ax plus 4a plus 13 is equal to 0. So since we know that this is equal to 25, then we know that a must equal 3, I think. Yeah, 12 plus 13. So we can actually get we have a concrete grip on what this is. It's that. Okay. Now, what am I actually trying to work out again? Use inequalities to define R. Can I just work out what R is? Something funny about this. Oh, it's to define R, the region R, not the area of R. So it actually, okay, so it is all the values of y such that y is less than the line but bigger than the curve C. Okay, I'll write it like that. I know it's not entirely accurate. So do we have what the line is, or do we have to work it out? I think we've got to work it out. So the line L then, well, its gradient, it goes up from 13, so it goes up by 12 in 2 steps. Its gradient is 6. So let's do y equals 6x plus 25. So we'll say y must be bigger than 3x squared plus 12x plus 25 is less than y is less than 6x plus 25. Doesn't quite feel right though, does it? Because that's 2 steps. Come on, let's do change in y over change in x. So 25, so that's 12 over 2, that is 6. And it passes through, so that must be it, you know. Just think what on earth it could be possibly be bigger than that, yet smaller than that.
Oh yeah, I see what you mean. Is that even physically possible?
Yeah, but this is hiding some so yeah, well, well, we must get some values of y. So let's do -1. Let's plug -1 into here. 3 times that squared plus 12 of that plus 25 gives us 16, and 6 of -1 plus 25 gives us 19. Yeah, so there are values there. It's this yeah, because when x is negative and small, it this creates a bigger negative than that. So
yeah.
So yeah, it's just, it doesn't. Yeah. Who's that, by the way?
Who's what?
Is that you, Creamer?
What are you saying?
Were you talking then?
No.
What? Somebody, okay, I think somebody's trying to screw with me there. Or it's Dan being Dan.
So no one else is in the Discord. Just me and you. Unless I said something and it just didn't sound like me.
Yeah.
Are we both going in a circle?
Were you talking about whether this is actually possible?
Yeah.
Oh right, okay. Yeah, you just didn't sound like you, and I was like, "What? Who the hell is that?"
Right.
Oh,
Okay.
And that's the
What's
whole
going on?
question. I'm like, yeah, have I got to the hallucination stage yet? It's a bit early for that, isn't it? Yeah, that was bizarre. That was slightly terrifying. Okay, a new smartphone is released by a company. The company.
I'll just keep changing my accent as I keep talking to you.
Please do. Okay, the company monitored the total number of phones N at time T days after the phone was released. Okay, so sold N phones. The company observed that during this time, the rate of increase of N was proportional to N. Right. So what it's saying is the rate of increase of N, so dN by dt, is equal to N. Oh, well, it's equal to Kn, so because it's proportional to N. So for N in terms of T, it should be some kind of exponential, right? Because, you know, when you differentiate an exponential, you kind of get the same thing back. So let's do this like an ODE, I guess. Integral of dn over n is equal to k times the integral of dt. So that means log n is equal to kt. So that means n is equal to e to the power of kt. And I probably could have, yeah, I probably should have just known that off the bat. And we'll put a constant on the end. Okay. What a bizarre little question that was. Was that question 8? Yes. So question 9. It's a weird little question. Okay, what is going on here? Some kind of distorted exponential. Okay, so it shows that equation where that, okay, show that its derivative is that. So let's just go ahead and differentiate it. So 4x squared minus 2 times minus 2e to the power minus 2x plus e to the minus 2x times 4x squared minus 8. The derivative of that is just 8x. Okay, so tidying up, we have, what form does it want? It wants me to pull out the e to the minus 2x. That's fine. So minus 8x squared plus 16 e to the minus 2x plus 8x e to the minus 2x. And then we pull out the e to the minus 2x and we get, oh, and it wants me to pull the 8 out as well. So 8, and then we get minus x squared plus x plus 2. Is that what it wants? Yes, it's just written the terms in a funny order. Okay, so that's fine. Hence find in the simplest form the exact coordinates of the stationary points of C. So if this is equal to 0, then it implies that either that is 0 or that this quadratic is 0. That is an exponential, so it can certainly never be 0. So x squared take x take 2 must be equal to 0. Come on, factorize. Come on, don't screw me over here. Yep, minus 2 plus 1. So x must be equal to minus 1 or x must be equal to 2. And that looks about right to me. We've got a stationary point here and a stationary point there. That distance looks approximately double that. Fine. The function g and the function h are defined by those. Find the range of g and the range of h. So, well, we know f of x, the range of f of x is that it's greater than whatever the value is at minus 1. So f of minus 1, let's work that out. So minus 1 equals 4 ans squared minus 2 times e to the power of minus 2 ans. So f of x must be greater than minus 30, let's say. So the range of g then, g of x must be greater than minus 60, because when you blow it out that way, we're going to reduce that minimum down to minus 60. And the range of h of x, well, that's going to be 3 less than that, so it's going to be bigger than minus 63. Fine. These questions are getting easier. Shouldn't speak too soon, of course. Oh god, yeah, spoke too soon. Fine. Ah, another substitution question. I suck so badly at these. Come on, let's do it. Hopefully it'll be nice because it is the A-level paper. It's not A-level further maths, so it shouldn't be anything too crazy. So we've got x is equal to u squared plus 1. That's a weird way to define it because usually you define it in terms of u, but I guess there's a reason it wants me to do that. So dx by du is equal to 2u. So in other words, dx is equal to 2u times du. Okay, so fine. So the integral for 5 between 5 and 10 of this is 6u du. So that's good. We've got this 6 up here, which is what we need. And then x minus 1 is u squared. And we've got a 3 plus, okay, so root x minus 1. I think that's just u, right? Because x minus 1 and then root, yep. So that is just going to be 3 plus 2u. And then we have got cancel. So this is the integral from 5 to 10 of 6 du over u 3 plus 2u. Oh, that was actually quite painless as far as substitutions go. Hence using algebraic integration. Algebraic integration, is there another kind? Lebesgue integration, I don't know. Show that it is log a for some rational. Okay, so we can go ahead and integrate that now. Okay, and how do we do that? Right, so this is 6 over u 3 plus 2u. It's the partial fractions game again, starring me. b over 3 plus 2u. Don't know what I'm talking about. 6 is equal to 3 plus 2u plus bu. So how many u's have we got on both sides? 0 is equal to 2a plus b. And how many constants have we got? 6 is equal to 3a. So a is 2 and b is minus 4. So this integral becomes the integral between 5 and 10 of now let's give ourselves some room to breathe. Let's go down here, 2, 5 and 10 of du by u plus negative 4 lots of the integral of this 1 over 3 plus 2u. Now we actually want the 2 up there, so I'm going to divide by 2 there. du. So this is 2 log u between 10 and 5 minus 2 log 3 plus 2u between 10 and 5. So this is 2 log 10 minus log 5 minus 2. Okay, wow. Log of 23. Now something does not feel right about that. What? Am I going insane? Yes, I am going insane because these are not the limits. So, you idiot. Right, ignore all that. We've got, so when x is 10, u is 3. And when x is 5, it must be 2, right? It would be very unfriendly to do anything else. Yeah, 2. So let's just change all these limits between 2 and 3. I mean, log of 23, there's nothing going on with that. You can't even, like, split that up into anything nicer. Where p and q are positive constants to be found. I didn't read the question properly. You know, shoot me. Log 3 minus log 2 minus 2. Lots of... Okay, so 3 times 2 is 6 plus 3 is 9. And that's a perfectly good number. 2 times 2 is 4 plus 3 is 7. Are you joking? I suppose, actually thinking about it, we are going to be compressing this all together into one log of something. So the 23 wasn't actually entirely unreasonable thinking about it, but it did tip me off that something was afoot. Minus 2 log, now 9 is 3 squared minus log 7. So we get 2 log 3 minus 2 log 2 minus 4 log 3 minus log 7. So this is minus... Oh, now what am I doing here? Yeah, nothing nice really happens with this. So actually, I'll tell you what, we'll do log 9 minus log 4 minus log 81 minus log 7. This does not feel right one bit. So we basically need to do 9 divided by 4, and then divide it by 81, and then divide the whole thing by 7. So we get log 1 on 252. What a bizarre answer to a question. Now, I do have the old calculator here, so I can actually do this. So it's gonna be 6 over x 3 plus 2x between 2 and 3. This should give me an answer of 1 over... Oh no, that's far too high. Okay. I don't like this log 7. There's something going on here. Oh, we need to add log 7 because I've not... this bloody... Okay, let's go from here. 2 log 3 minus log 2 minus 2 log 9 plus log 7. So we get log 9 take log 4 take log 81 plus log 7. So this might be slightly nicer. So we need to do 9 divided by 4. In fact, what was that answer? So the actual answer is something around 0.308. Let's bear that in mind. So we get 9 divided by 4, divide it by 81, and then multiply it by 7, and we get... still not right.
So Catherine said change the limits, but that was the mistake you noted before, right?
Yeah. I think I've got that. Yeah. Just making some kind of error around here. What am I doing wrong?
Catherine's saying 2 log 7.
Oh god, not again. Yeah, it is.
Well, you've expanded the bracket.
Yeah, it's because just kind of trying to hurry and making more mistakes and costing myself more time. So yeah, that's 49 there, isn't it? Yeah, 49. Yeah, thanks, Catherine. So 9 divided by 4 divided by 81 times 49. But that's even worse. Still nowhere near the right answer here. Oh, this is doing my head in, honestly. That's even worse. So I might just leave it. I can't figure out.
Maybe come back to it. I don't know. Gee.
Right. So 2 over u minus 4 over 3 plus 2u. Is that right? So what I usually do here is I choose a random number like 17 and I do 6 over that 3 plus 2 that. So we get 6 on 629 when we substitute 17 into that side. And then I want to get the same on this side, so 2 over ans minus 4 over 3 plus 2 ans. Okay, so this is right. So when I integrate, I do 2 between 2 and 3 of du over u minus 4 times the integral of du over 3 plus 2u. The problem being that we need the derivative of the numerator on the denominator. So it needs to be a 2 here. But I can't just create a 2, I need to divide by 2. So it is 2 times the integral 1 over u du minus 2 integral 2 over 3 plus 2u du. And that is 2 log u. And that is subtracting 2 log 3 plus 2u. And I am doing it between 2 and 3. So 2 log 3 minus 2 log 2 3s is 6 plus 3 is 9. Subtract 2 log 2 minus 2 log 2 times 2 is 4 plus 3 is 7. So log 9 subtract log 81 subtract log 4 plus log 49. So that is 9 divided by 81 divided by 4 times 49. What on earth am I doing wrong here?
Catherine's saying she thinks it's correct.
Well, either this is correct, or I must have done the calculator thing wrong.
She's got the same answer as, well, she put the same answer as you. I don't know if the log 49 over 36.
Yeah, okay, maybe it is right. Maybe it is right. Let's do, just out of curiosity, let's do 3 over x minus 1, 3 plus 2 root x minus 1, and that is between 5 and 10. Now, actually, there is something that can go awry here. Yeah, 0.308. So the problem with doing it on the calculator like this actually might give you the wrong answer if the if it dips below the axis. So if you've got something that looks like that, then the total integral is going to be that, subtract that area, whereas the calculator doesn't always give you, it doesn't always sort it out. And we did log 49 on 36 for some reason. Oh, okay, and that is 0.308. So actually,
yeah.
Okay, okay, all right, okay. We can get away from me. Let's start another question. Okay. So.
Yeah, Catherine just put that as well seconds before you said that as well. So you're on the same page.
Right. Okay. Perfect. Perfect. Okay. So we could be confident that we are still sane, at least somewhat. Jeez. Okay. This looks like a great little question. This reminds me of. Have you seen like the Mandelbrot set? It looks kind of reminiscent of that.
No idea what you're talking about.
Just Google it. Mandelbrot set. It's one of the most beautiful things in all of mathematics.
All right.
So we've got two circles here.
Oh, fractal.
Yeah. I think you'll have seen it. You just don't know it by name. But yeah, it's pretty awesome. So what have we got here? We want to find. Now in the Mandelbrot set, these circles are kind of tangential to each other, so it kind of goes in forever. But obviously here we're meeting at a kind of. This is a weird question actually. I don't think I've ever seen this where these circles are kind of smushed together like this. Okay, so we want angle AOB, which is this angle here. So right in there. Okay, we want to show that it's that. Well, we know that circle 1 has a radius of 10. This is going to be some kind of cosine rule question in disguise, isn't it? All we need to know is this length here. Or we could know that length there. So we need the points where they intersect, okay? I don't think there's any way around that. So we know y squared is equal to 100 minus x squared. So x minus 15 all squared plus 100 minus x squared is equal to 40. This will give us the x coordinate. So x squared, take 30x plus 225 plus 100 minus x squared is equal to 40. Now, curiously, the x squareds cancel here. I would expect two solutions to this because they intersect in two different places. But the x coordinate of both the intersection points are the same. So, indeed, we should get cancellation. So, fine. So, what is 40 take 100 take 225 is 285. Would have expected a 9. I've not messed up that 15 squared, have I? No. Fine. 40 take 100 take 225 and then divide by 30. So x is equal to 9.5 or 19 on 2. This is the kind of question where the decimal might actually be easier. So we know that that is the x coordinate. We actually don't need the y coordinate, not yet anyway, because we've basically got a triangle here. That's theta on 2. 10, 9.5. So cos of half theta is equal to adjacent over hypotenuse. So theta on 2. And we do want to be in radians. We are in radians. So inverse cos of 9.5 on 10 is that. Then times it by 2. We get blah blah blah. Theta is equal to 0.635, which is what it wants. Good. Fine. The region shown shaded in figure 3 is bounded by, find the perimeter of the shaded region. Lovely, lovely question. Yeah, I got all the time in the world for this. I'm a big fan of this guy. This is good. This is good stuff. So, we want basically the circumference of circle 1 minus that arc there. So we get rid of that. And then we want the circumference of circle 2 minus that arc there. So it is the circumference of C1 minus, let's call this arc A1, let's call this arc A2, minus the length of A1, plus the circumference of C2 minus A2. That is what I will go with here, I think. Okay, so we just need to do it now. It shouldn't be too bad. So we know that this has radius 10. We know that this has radius root 40. So the circumference parts are easy enough to work out. So this is 2 pi times 10 minus A1 plus 2 pi root 40 minus A2. Now the arc here is just r theta, and we worked out, so that's 10 theta, 0.625, 35, what we worked out before, which is 6.35. So we can substitute in, so we've got 20 pi minus 6.35 plus 2 root 40 lots of pi minus that arc A2. So the arc A2 is the only bit that we need to think about. Now, is there a clever way of doing this? So we are looking at that, aren't we? We're looking at that where we've got root 40 here, and if we want that, let's split it like that. So if only we knew that or that. Okay, and I think we can work this out actually here, because we know So this is the coordinates of the points of interception, and we know y squared is equal to 100 minus x squared, and we found that x was it 9.5? 9.5. So this is so y is equal to root of 100 minus 9.5 squared, and we do get two answers for this. We're going to take the positive one. So root 100 minus 9.5 squared. So it's root 39 on 2. Let's stick with that for now. Root 39 on 2. Let's give it a different name. Let's call this whole thing phi. So again, we've got sine this time. Sine of half of phi is equal to the opposite, root 39 on 2, divided by root 40. Okay, so therefore phi is equal to, we've got inverse sine of root 39 over 2 root 40. And then we double it. And we get 1.03. Now, does that make sense in the context of the question? Yes, it should be more obtuse. It should be a bigger angle than this one, because it's squished in here. So now we just need to do our phi for A2. So that's root 40 times this horrible thing, which actually, oh yeah, fine, 0.033. So times that by root 40, and we get 6.53. So only slightly bigger, but that kind of makes sense. Okay, so we have got 20 pi plus 2 root 40 lots of pi. Take 6.35, take 6.53, and we get 89. 89. So 89.69. What a great question. I'm sure you agree.
Of course.
Of course. You don't have the energy to disagree with me. No, it is good though.
I know what you mean. I remember doing those kind of questions and finding them very satisfying.
It's even more satisfying when it turns out to be a nice answer, you know, not 89 point crap.
Yeah.
So, you know, 12A then. So this looks like your standard issue trig identities sort of question. So we want to show that cosec theta minus sine theta. So we want to play around with this, do we? So this is 1 on sine theta. So we're going to subtract sine squared theta on sine theta, which is cos squared theta on sine theta, which is cos theta times cos theta on sine theta. Just looking ahead to the answer, it wants me to get that cos theta out times cot theta. Okay, easy enough. B, hence or otherwise, solve. Okay, so it wants us to solve. So we've just worked out that is equal to that. So we've got cos x, cot x is equal to cos x cot 3x minus 50. Okay, now we are told that x is strictly between these values here. So can we just divide by cos x? I don't think we can, you know. So let's be grown-ups about it. Let's do it properly. We'll do cos x cot x minus cot 3x minus 50. So this tells us that either cos x is 0, in which case we generate an answer of x equals 90, I think. Oh no, I'm way off on that. Come on, cos. Oh, we're in radians. Sorry. Apologies all around. So cos 90 is 0. Yeah, okay, wasn't losing my mind. And that's the only such solution between 0 and 180. So we'll park that one for now. The other answer is telling us that cot x minus cot 3x minus 50 equals 0. So cot x is equal to cot 3x minus 50. In other words, let's change this into tan, because it's just a bit easier, because cot is 1 over tan x, so we can times up and blah blah blah. 3x minus 50. Okay, now there's a trap here, I believe, because it is not as straightforward as just then saying 3x minus 50 is equal to x, because we could have the x plus 180 and things like that. So we've got to be careful. So 3x, so let's just set this out over here. So 3x 50, it could be equal to x, but because tan is a periodic function, it repeats every 180 degrees, it could be the case that 3x minus 50 is equal to x plus 180. We could even have x plus 360, so we'll bear that in mind. So what have we got now then? We've got that 2x is equal to 50, so x is equal to 25. We've got x, 2x is equal to 180 plus 50, which is 230, so x is equal to 115. Let's see if this gives us a valid solution. I'm suspecting not, because now we get 2x is equal to 410, and therefore x is equal to 205. Bad, it's outside of the range. So our solutions are 25, 90, and 115. Happy with that? Okay, paper. Question 13. A sequence of numbers is defined by that. Okay, now that's a funny looking sequence, I've got to admit. K is a constant, given that this, okay, so the sequence is a periodic sequence of order 3. You don't really get many of these. That's interesting. I've never seen a question like this before, I don't think. So, a lesson here for anyone who's taking exams. If you encounter something you've never seen before, you've got to keep calm, and you just got to use the information that you're given. So, what do we know? We can work out what A2 is. So, this because we know that A1 is equal to 2. So let's use that piece of information. It is equal to K 2 plus 2 over 2. So that is equal to 2k. Fine. And then we know that A3, we just substitute in 2k into here. So k, 2k plus 2 over 2k. So that is equal to cancel k plus 1. And then we know A4 is equal to, we'll substitute k plus 1 into there. K plus 1 plus 2 is k plus 3, all over k plus 1. Okay, now, because it's periodic, so this is the point where we might get stuck, but we remind ourselves, you always use the information. You know, if you get stuck, just ask yourself, what information haven't I used yet? So we haven't used the fact that it's periodic. That means that every 3 terms, it repeats itself. So A4 must be the same as A1. So in other words, k plus 3 over k plus 1 is equal to 2, as A4 is equal to A1. Okay, and now we just expand this whole thing and we get that, which when we tidy up, we get that. And that's what it wants. That's fine. B, for this sequence, explain why k can't be 1. Well, presumably we get k minus 2k plus 1, so k equals minus 1 and k equals 2. So usually what happens here is, oh, hang on a minute, I've got those signs rolling around. So we get k equals plus 1 and k equals minus 2. So it's asking why to reject this one. Now usually when you have something like this, it means you end up dividing by 0 or something. Can't really see why that's an issue here though. But what is an issue is a1 equals 2, right? If k was equal to 1, then we'd get a2 equal to 2 and a3 equal to 2. So that means its period would be 1, where we know that its period is 3. So that is a contradiction. So we know that k must equal -2. Find the value of the sum up to 80 of that sequence. Okay. I think we can do that, can't we? So, right, let me just get these out. So we know that the sequence goes 2, 2k, k plus 1, and then it repeats itself. So it's 2, -4, -1. So does that make sense? Because now -1 plus 2 is -1 plus 2 is 1 times -2 is -2 divided by -1 is 2. Yeah. So the sequence repeats itself there. Now if we want to sum up from 1 to 80, so we do a1 plus a2 plus a3, and then when we do the next three terms, a4 plus a5 plus a6, that is actually going to be the same sum. So if we call that S1, that is also going to be S1. And that is going to be true all the way up to, what's the multiple of 3 that's just below 80? 78. So A78 plus A77 plus A76. So that's right, isn't it? So we get 26 of these. So 26 of these. And then we've just got a stray A79 and A80 left over. A79 is equal to A1 and A80 is equal to A2. So what is the sum of these? So 2 take 4 take 1 is -3, isn't it? So -3. So we need 26 -3s, and then we add A1 and then we add A2. So 26 times -3, add 2, take away 4 is -80. -80. Okay. Now I wonder if I can do this on my calculator. So it's equal to -2 x plus 2 over x. No, because it's a recursive thing, so it doesn't work like that. Fine, whatever. So happy with the -80. It's fine. And we are on last question of this A-level paper. These papers just go on forever, don't they?
Yeah, it's very long.
Back in the old days, you know, when it was like 10 questions a paper, it was so much easier. But arguably too easy. And we're going to finish on an ODE, and that's what I finished on. I think last time I did one of these. The very, very last question, about 10 in the morning, I finished on an ODE, and it was a total nightmare. I hope that's ink and not blood on my hands. I think it's ink. It's fine. So a large spherical balloon is deflating. You know, talk about excitement. What more do you want from these questions than the large spherical balloons deflating? At time t seconds, the balloon has radius r and volume v. The volume of the balloon is modeled as decreasing at a constant rate. Okay, let's just mathify that first of all. So it means dv by dt is equal to a constant k. Using this model, show that dr by dt is equal to that. Ooh, okay, well, we know the volume of a large spherical balloon is 4/3 pi r cubed, which means dv by dr is equal to 4 pi r squared, which is the formula for the surface area of a sphere, actually. We want dr by dt. So this is going to be dr by dv times dv by dt. So we know dr by dv is 1 over 4 pi r squared, and we're timesing by dv by dt, which is our constant k. Now there's no pi's involved here, so I think what I should have done is, this is a decreasing constant, so it wants k to be positive. Yeah, k is positive. So if it's decreasing, we'll just put that minus there. And in fact, I'm going to call it k prime, because we're going to engulf there's no pi's involved here. But we've got minus k prime over 4 pi multiplied by 1 over r squared. Now we let k equal k prime on 4 pi. 4 pi is a constant, so we can just dissolve all of these constants together. So this is equal to k times 1 over r squared, k over r squared, minus. Okay, so that's all fine. Given that the initial radius of the balloon is 40, right? So we are going to be solving this ODE because so radius is 40 at t equals 0. That's an initial condition, and we're given a boundary condition as well. So at t equals 5, the radius is 20, and the volume of the balloon continues to decrease at a constant rate until the balloon is empty. That's sad, isn't it? Okay, so solve the differential equation. So this is your standard issue times both sides by dt type of ODE, which, you know, isn't technically correct, but it's correct enough for us. So the integral of r squared dr is equal to minus k times the integral of dt. So r cubed divided by 3 is equal to minus kt. And do we care that we have another constant here? I suppose we do, because this one is proportional to t, and the other constant is going to be down to the initial conditions. So we do need to take that into account. Let's just call it c, because I'm not going to do anything extra with it. Using the initial condition of t equals 0 and r equals 40, we get that c is 40 cubed, which is big, divided by 3. And let's leave it like that, 64,000 over 3. Okay, so r cubed over 3 plus kt is equal to that big boy. And now we know when t equals 5 and r equals 20, 20 cubed is 8,000, isn't it? Let's just double check that. 8,000, so 8,000 on 3 plus 5k is equal to 64,000 on 3. Okay, so 64,000 minus 8,000, all divided by 15, because I've times through by 3, take that over, divide by the 15, so we get k. Oh, another nasty piece of work, that. Okay, so our equation linking r and t, I suppose, is r cubed on 3 plus 11200 on 3. T is equal to 64,000 on 3. Now, it definitely makes sense here to times through by 3. So r cubed plus r cubed, slow down, plus that is equal to that. Okay, so doesn't want it in any particular form, so that's fine. Find the limitations on the values of t for which the equation is valid. So basically, when does this fall apart? Well, r must always be positive because it represents the radius, so it's a physical measurement. So that means r cubed must always be positive. So since r cubed is equal to 64,000 minus 11200 t, and we're saying that must always be positive, then that means that t must always be less than 64,000 over 11,200. So t must be less than, I suppose we don't even need to work this out, but let's do it anyway. It's the last question. Let's go crazy. 40 on 7. In other words, 5.7. And I suppose what that represents is after 5.7 seconds, the balloon is deflated, isn't it? Is that what it means? Yeah, of course, because when r is 0, so when it's actually finally deflated, then that's what we get as our t. So it takes 5.7 seconds to deflate. So that's the end of that. That was actually fine. Apart from that logs question with the integration, there's a question 15. You are joking.
That's brutal.
Oh no. Oh man, I feel like all my students who never check like the back page, where you give them a test and there's questions on the front, there's questions on the back, and you get one student there who's like sitting pretty after 10 minutes, and then you go over there and say, "Are you sure you checked your answers?" and you turn over the page, and then they just, I tell you what, they deflate quicker than a large spherical balloon. Is how quickly they deflate. So.
Yeah.
I apologize. Anyway, fine.
I mean, it's fine.
It's fine. It's
fine.
It's fine. All right. So some implicit differentiation now. So we've got x squared sec squared y dy by dx. Don't usually have to pull that one out. Plus tan y times 2x is equal to 9. Okay, and then we just want to rearrange for dy by dx. Now, the only problem with that is that we've got a load of horrible stuff in here that simply does not belong. So, what are we to do with that? Well, I recognize we've got x squared plus 9 squared downstairs there. So I'm thinking, instead of differentiating implicitly, we should do tan y is equal to 9 over x squared, which is equal to 3 over x squared, and then y equals arctan of that. 3 over x. 3 over x squared, isn't it? Now, when we differentiate that, oof, what on earth are we looking at here? Right, so I'm going to do a little trick here. Let big X equal 3 over x all squared, and we'll worry about it later. Hope this works. Right, well, this should differentiate to 1 over 1 plus x squared. But that isn't going to give me what I want, I don't think. So, what to do? What to do? Well, we could try it. Yeah, because I get 9 over small x squared plus, so that could be x squared over x squared all under 1. So I get... Eesh. No, I'm doing it wrong here. There's something wrong about how I'm doing. Actually, because x squared therefore is 9 on x squared squared, which is 81 on x to the power 4. So 1 plus 81 on x to the power 4 is x to the power 4 plus 81 over x to the power 4, which is x to the power 4 over x to the power 4 plus 81. Now, I'm just not getting this minus 18x part. That's what I'm not getting. So, what to do? I am going to consult our formula sheet here because I'm not applying that derivative correctly, I don't think. Something is going wrong there. So, where is it? So, differentiates to 1 over 1 plus x squared. Yeah, okay, so I've got a problem here. Tempted to try the implicit way one more time. Yeah, okay, forget about that. Let's do it the implicit way. So x squared. Oh, actually, this is going to work really well. Actually, so dy by dx, because I've completely forgotten that we know quite a lot about the tans. So that, so we know. So sine squared plus cos squared equals 1. Now, if I divide through by cos, I get tan squared plus 1 is equal to sec squared. So we can do x squared 1 plus tan squared y dy by dx plus tan y times 2x is equal to 9. But the point is, we know that x squared tan y is equal to 9. So tan y is equal to 9 on x squared. So that's what I can put into there. And tan squared y is equal to 81 over x to the power 4. Okay, this is looking better. So x squared 1 plus 81 over x to the power 4 times dy by dx plus tan y 9 over x squared times 2x. And that's where our 18 is coming from. So this is looking good. And actually, this whole thing is equal to 0 because I've found the derivative there. So, silly me. So what have we got? We've got x squared plus 81 over x squared, which we'll call x to the power 4 over x to the power 4 there, because I'll want that quartic bit to stay with me. Equals, so cancels, minus 18 over x. So dy by dx is equal to minus 18 x to the power 4 over x to the power 4 plus 81, and that cancels with that. But bizarrely, I've ended up with a cubed bit on the top there, which should be just minus 18x. So I'm close. Where have I gone wrong now? I think where I've gone wrong is in when I bodged through that. So let's just take one more look at that. X squared times 1 plus 81 over... It didn't feel right when I did it. I should have took my time. X squared plus 81 over x squared. Yes, because it's the cancellation. So this is now x to the power 4 plus 81 over x squared, not over x to the power. So that's only an x squared there. So that becomes x squared, which cancels down to 1. Yeah, so minus 18x over x to the power 4 plus 81. Okay. Now, I think you can do it using the arctan way. I'm not familiar enough with how to do it. So this is a problem that happened before when I was talking to James, I think, where it doesn't quite work the way you expect it to. You can't just treat that x as that and expect it to work. There's more machinery going on there. Fine. Prove that C has a point of inflection at that value there. Well, points of inflection occur when the second derivative is 0. So we need to, I need to find the second derivative. Fine. So, okay, what are we thinking then? Product rule. I think I'm going to go with product rule. We're doing our usual x to the power 4 plus 81 to the minus 1. That's how I'm going to do this. I'm not going to use the quotient rule. I think it's a little bit too meaty for that. Although it's basically the same thing. Okay, so oh no, you know what? I'm gonna go quotient rule. I've changed my mind. So d2y by dx squared, which is equal to 0, is equal to so it's x to the power 4 plus 81 times minus 18 minus minus 18x times the derivative of the denominator 4x cubed. And it's all over x to the power 4 plus 81 squared. We're getting some monstrous powers in here. Okay, so this is now equal to minus 18 x to the power of 4. Geez, what's 18 times 81? Must be something like 1458 minus 1458 plus 18 times 4, 72, plus 72 x to the power of 4 over the downstairs, which I don't care about because it's equal to 0, so when I times up, it dies. So 72 minus 18 is 54. So I've got 54. X to the power of 4 is equal to 1458. Please be 27. 1458 divided by 54 equals 27. Yes, yes, yes. So x is equal to the 4th root of 27, which is what it says there. So we are done. And don't you dare tell me that there is a question 16 to this paper. Oh my god. I can't believe it. There's actually a question 16. Right. You're muted, Creamer, but probably for the best because your reaction is probably as disappointed as mine is. Okay, prove by contradiction. All right, so proof questions should be easy enough. There are no positive integers. 4p squared minus q squared equals 25. Okay. Well, it wants us to prove by contradiction. I'm not sure it's the only way of doing it. So assume there exist p and q naturals such that 4p squared minus q squared is equal to 25. Okay, so we've made the assumption. Now, what can we do with it? Well, yeah, what can we do with it? Well, okay then, so suppose let's just play around with this. So 4p squared is equal to 25 plus q squared. Interesting. Because that is now 5 over 2 squared plus q over 2 squared. This looks difference of 2 squaresy. So this is saying we've got 2 squares that add to another square. Oh, you know what? No, let's do it the other way. We've got 4p squared minus 25 is equal to q squared. Now, that is a difference of 2 squares. So that's 2p minus 5, 2p plus 5 is equal to q squared. So what is going wrong with that? Why aren't we allowed to do that? There's gotta be something in that. Gotta be. Can the difference of 2 squares ever be another square? Yeah, of course it can. You know, you've got 25 minus 16 equals 9. Yeah, of course. So... what we want to eventually... oh God, I thought this would be easy, actually. What we want to eventually happen is we want to get to the stage... the other way, I suppose, is 2p minus q, 2p... ah, here we go. Here we go. So that is equal to 25. If we do the difference of 2 squares on that, then we get that. But... the only way to factor 25 is as 25 by 1 or as 5 by 5. So either we've got this is equal to 5 and this is equal to 5, and we'll get a contradiction here surely, because this is going to imply that q is equal to 0 and p is equal to 5 halves, which is a fraction which you can't have, but let's go through the motions anyway. So we get that. So that means that 5 plus q is equal to 5 minus q, which means 2q is equal to 0, so q is 0, and p is equal to 5 over 2, which is not an integer, so that is a contradiction. Or we could have the case where we factor this into 25 and 1, so 2p minus q is, I mean, surely smaller, that is the smaller one, so that has to be the one, since p and q are both positive. And then 2p minus, plus q is equal to 25, and then we'll see what contradiction erupts from this. So if we do this one, subtract this one, we get 2q is equal to 24, so q is equal to 12. Let me guess, p turns out to be not an integer. So 2p minus 12 is equal to 1. So we get p is equal to 13 on 2, which again is not an integer, which is a contradiction. And there, surely now, we have done it. We have done it. It is the end of the paper. There is no question 17. Man, I thought it was done after question 14. Shock twist, there was a question 15. And even more shocking, there was a question 16. But it's done. It is done. So, wow. I'm really short on time, and I'm starving. I need to get some food. I think what I'm going to do. I don't know if you're there, Creamer. I can't hear you if you're there. I'm going to be back in a few minutes. I'll just put a note here that says BRB. Well, I'm going to put some rice on. I'll do some papers while that's cooking, and then I can eat some food later. Oh, are you there?
Yeah, can you hear me now?
Yeah, I can hear you. Yeah.
I don't know what's going on there. Yeah, my headset's obviously just being weird.
So, how about that surprise question 16, man?
Yeah, that was brutal.
I couldn't believe it. Honestly, couldn't believe it. Oh, God. All the papers before, they ended at like question 14. So, when there was a 15, I just wanted to shoot myself. And then when there was a question 16, I wanted to shoot myself all over again. Luckily, it was a proof question, so it was quite fun.
Yeah, well, you did it pretty quickly. It's good.
It's in my wheelhouse. So I don't know if you heard that. I'm gonna put. I take it you wanted to leave at some point.
Yeah, I'm gonna head off now. Yeah.
Yeah, that's absolutely fine. Thanks very much for staying up with me.
Yeah, no worries. I'm sorry I couldn't have been more engaging with the actual maths, but
no, it's absolutely fine. It's sometimes good to just have a bit of input and a bit of someone watching the comments.
All good.
Catherine here picking up on a lot of mistakes I made, so good to draw attention to that. Okay, so
all right, well, best of luck. Yeah.
Cheers.
Stay strong.
And
I'll see you in the morning.
I'll speak to you tomorrow, no doubt.
Okay. All right.
See ya. So, nobody on the call with me at the moment, so I might go quiet and just try and focus and grind through a few of these papers. So I've got some IGCSE papers now. The IGCSE, that stands for the International GCSE. So that is the international variant of the paper taken by the 15 to 16-year-old students in the UK. The international variant being the paper taken by overseas students, I believe. Again, split into the higher tier and the foundation tier. So I've got the higher tier here. Now what I actually found is there's the two papers for the standard GCSE, and there is a GCSE further maths. So that is like a bridge between the between GCSE and A level. So let's start with that further one. Let's get that out of the way. I'm very conscious of the fact that I'm not even halfway through the number of papers yet, and yet I'm hemorrhaging time here. So I might just need to go quiet and focus, but I'll try to add little bits of insights as we go for those who are still watching. So let's do it. Calculators may be used. Right. Now, I've honestly, I've never even seen, I didn't even know that the IGCSE did a further maths, so I've got absolutely no idea what is going to be on here. I'm expecting it's going to be like the usual further GCSE further maths, in that it has a little bit of calculus, it has a little bit of factor theorem, that sort of thing, nothing too crazy, but we shall see how it goes. Right, it starts at least by telling us that there are 11 questions, so there shouldn't be any nasty surprises when we get to question 11. And anyway, okay, so there's radians on here, so it's introducing grown-up angle units. For those who don't know, if you've got a circle, then you know that to measure all the way around is 360 degrees. Well, radians, you say, instead of splitting it up into 360 pieces and each individual piece is 1 degree, you say all the way around is 2 pi. Okay, so it seems like a very unnatural thing to do until you realize there's a very natural way to define what a radian is, and that is if you've got a sector of a circle of radius 1 with arc length 1, then that there is what we call 1 radian. And it's a very natural way of measuring angles, and it is the way to measure angles. 360 is just plucked out of thin air. Why 360? There's no good reason for it. In fact, the gradient, which you might have seen on your calculator, that splits the circle up into 400 and says one gradient is just a 400th of the whole way around. So it's completely arbitrary, whereas this isn't that arbitrary, you know. There's this very special kind of relationship here, and when you define it this way, it turns out that a full turn is 2 pi. Okay. Anyway, like I said, I need to just concentrate here instead of discussing the maths. So anyway, right. So we have got that the area of the sector, which is half r squared theta, is equal to 25, and we are told what r is. So that means that 50, so theta equals half. Okay. And the length of the arc AB. So r theta is the length of the arc. That's the other nice thing about radians. It's all natural. You know, you don't need to divide by 360 or any nonsense like that. So that's just 10 times half, which is 5. Okay. I'll do. That's 1 out of 11 questions. I've just realized I've not updated my exam counter here. Let me do that. So this is exam 11 of 24. Sorry, exam 12 of 24. So this will mark the halfway point. Is that right? So if this is exam 12, then yes, that's right. Sorry about that. So the equation has roots alpha and beta. Without solving this equation, form a quadratic equation with integer coefficient that has those roots. Oh boy. Okay. So, we know from the factor theorem that this quadratic will look like this. So if we expand that out, should be fine. Okay, yeah, this is interesting. Okay, so x squared subtract alpha plus 1 over 2 beta, lots of x, subtract beta plus 1 over 2 alpha, lots of x, plus alpha plus 1 over 2 beta, beta plus 1 over 2 alpha. This is quite a hefty question, I have to say. How on earth are we going to tidy this up? So x squared, take x, lots of alpha plus beta plus 1 over 2 beta plus 1 over 2 alpha, plus, so that's alpha beta, plus, so alpha times 1 over 2 alpha is a half, so plus 1 over 4 alpha beta. Okay. Right. Now what? So we haven't used this yet. So what can we do with that? So we know that so if we make this like this, then we know that x minus alpha, x minus beta has to equal that, right? Ah, okay, now we're getting somewhere. So now that tells us that minus alpha minus beta is equal to 5 on 3. So alpha plus beta is equal to 5 on 3, and it tells us that alpha beta is equal to 4 on 3. That is actually a rule that, now that I see it, the product of the roots is always 4 divided by 3, and the sum of the roots is always that divided by... Now, have I got the sign the right way around here? So I'm going to do minus alpha minus beta is equal to minus 5 over 3. Yeah, alpha plus beta equals 5 thirds. So, okay, fine. So x squared, take x. So alpha plus beta is 5 thirds. Now we've still got this to worry about. So this is going to be times by alpha times by beta. Alpha plus beta over 2 alpha beta. And we can sort that out because we know what alpha plus beta is, we know what alpha beta is. Plus alpha beta, which is 4 thirds, plus 1 over 4, 1 over 4, 4 thirds. Jeez, this is a nightmare. X squared, take x, lots of alpha plus beta is, so 5 thirds plus 5 thirds over 2 times 4 thirds, 8 thirds. Jeez. 4 thirds plus 1 plus 3 over 16. Okay. Calculator time. 5 thirds plus 5 eighths is 55 on 24. X squared minus x, 55 on 24 plus 4 thirds plus 1 plus 3 over 16, and that's 121 on 48. Okay, so we can times through here and do 48x minus 110x plus 121 is equal to 0. And I think that'll just about do it. Boy, I'm not gonna lie, that was quite tough. Just algebraically tough for someone who's basically 16. So question A then. So in a triangle ABC, AB is 12. Let's do a little sketch here. BC is 9. And we know BAC. So BAC is about 42. And we don't know where C is, do we? So, okay, and that's the point, because we want the two possible. I like this question. So we could have a 9 centimeters, or we could have a 9 centimeters. It's this sort of idea, basically showing that angle side side is not a rule for congruence, isn't it? You know. So 9 and 9. So we want theta, and we want phi, let's say. They are the angles. So we know that oh, jeez. I just thought 9 over. Yeah, I'm just thinking, do we want to use the sine rule here? That over sine 42, that over sine theta, we don't know what that is. Is my diagram right? Oh no, BC is 9. So we've got 9, oh yeah, sorry. So AB is that, but AB is always opposite that, isn't it? Which is just awkward. So 180 minus 42, 138. So this is 138 minus theta, and this is 138 minus phi. Okay. Sine 138 minus theta over 12 is equal to sine 42 over 9. I think that's the only way of really doing it. It's just awkward. So 138 minus theta is equal to 12 sine 42 over 9. Now, what is sine 42? And we're back into degrees here, aren't we? Sorry. Oh, wait, sorry. 12. No. Sine 42. I'm losing my mind here. Yes, so shift sine of 12 sine 42 over 9 is that. So 138 minus theta is equal to 63.15. But it's also equal to that, 116.85. Yeah, because sine graph, blah, blah, 180 minus. And so theta is going to be equal to 138 minus the first. So 138 minus 63.15 is 74.85. That's one possible angle. 138 minus 116.85 is 21.15. Okay, both acute, which looks about right to me. So that's 74.9, 21.2 to, oh, it wants it to do significant figures, so 75, 21. Okay, good question actually, I appreciate that. So, the graph shows that awkward looking graph, expressed as a single fraction. So this is going to be, we want that to be 2x squared, so that's going to be 2x cubed minus 1 over 2x squared. Hence, use the graph to obtain to one significant figure and estimate for the value of the cube root of 0.5. Yes, so 2x cubed minus 1 over 2x squared. When that is equal to 0, then x cubed is equal to, so this is when y is 0, is equal to 1/2, because that times up and dies. We add 1 and then divide by 2, so therefore x is the cube root of half. So, in other words, it's when y is 0, so 0.8. Okay, and I definitely did not cheat by using the calculator to try and figure out what to do on that question. By drawing a suitable straight line on the grid, find an estimate to two significant figures for the root of the equation that. So, this is 4 is equal to 2x minus 1 over 2x squared. Oh, which isn't what we've got here. So let's take 1x back over to that side, x minus 2 over x squared. So 4 minus x, y equals minus x plus 4, as we call it. So it's a gradient minus 1 with y-intercept of 4. So it looks something like, God, my lamp and everything is in the way. I'm struggling to get this accurate enough. That'll do. So it looks like, what does it want? Two significant figures? I don't know. 2.52. I'm gonna say, what is that? That's 3. That's 2.2. That'd be 2. Yeah, 2.12. Yeah. Okay. Okay, so there is a bit of calculus on here. So we need to integrate this. So the integral of that will be 3x minus x squared on 2 minus, oh god, x minus 3. So add 1 to that. We get x to the minus 3, sorry, minus 2 divided by 2, and hence evaluate that. So between 2 and 1, 3 of 2 minus 2 squared on 2 is 2, minus 1 over 8. Subtract 3 minus half minus a half, I guess. So it's, that whole thing is 4. So 6 minus 2 minus 1/8 minus 4. So the whole thing is minus 1 over 8. Let me check that on the old calculator. So 3 minus x plus 1 over x cubed and that's between 1 and 2. Come on, 15x. I knew that was going to be wrong. Oh, no, 3 take a half is subtract 2 at the end. So I need to, I've overcounted that by 2, so I need to add 2 to that. So that's minus 1 plus 16 over 8, which is 15 on 8, which is right. Okay, and then B, I find the integral of 6 sine 3x. So that is minus 6 cos 3x on 3, which is minus 2 cos 3x. And hence evaluate that. So it's minus 2 cos 3 pi by 6 minus minus 2 cos 3 pi by 9. So into the calculator, minus 2, okay, we're in degrees, radians again, minus 2 cos 3 pi by 6 minus 2 cos 3 pi by 9. 1. Nice. Always nice to finish with a 1. Okay, alright, some asymptotes here. So a part 1, asymptote on the x-axis is going to be x is equal to, so x cannot be 3. So the one that's parallel to the x-axis is actually the other one. So so the one that's parallel to the x-axis is y equals 2, because as this blows up to infinity, then the whole thing dissolves into y equals 2, and the one parallel to the y-axis is x equals 3, because x cannot equal 3. Find the coordinates at the point where c crosses the x-axis. So that's when y is 0, is equal to 2x minus 4 over some stuff which dies, so x is equal to 2. So 2, 0 is the coordinate. Where it crosses the y-axis is going to be at 4/3. So that's 0, 4 on 3. Just substituting x equals 0 into there. Sketch showing clearly the asymptotes and blah blah blah. So we cross at 2, and we have an asymptote at 3. We cross at 4/3. Okay, so I'm figuring we've got a branch that goes down like that, but we'll see. And then the other asymptote is at y equals 2. Let's do it there, not drawn to scale at all, it's just a sketch. So, you know what, let's treat ourselves to a different color for this. So one branch is definitely going to go up like that, and then the other branch is going to go kind of down through these points like that. Close enough, I would say. Alright, okay, so much paper. Okay, a particle P moves along the x-axis so that at time t seconds, the velocity of P is given by v cos 2t. Find the value of t when P first comes to instantaneous rest. So it's when the velocity is 0. So 5 cos 2t is equal to 0. We're doing calculus, I guess, so radians is probably the way to go. So inverse cos of 0, and then divided by 2. So t is equal to 0.785 seconds. B, find the magnitude of the maximum acceleration of P. So acceleration is dv by dt. So that is going to be minus 10 sine 2t. So there's going to be a maximum when this is 0. In other words, oh no, we want when this is biggest. So when this is biggest is when sine 2t is at minus 1. So 10 is the is that. Okay, so at t equals 0, p is at the point A, where OA is 0.2. Okay, 0.2. When t first comes to instantaneous rest, p is at the point B. Calculate the distance OB. So okay, the position is given by the integral of v dt. I guess I was maybe thinking about wanting to do this. 5 sine 2t over 2 plus a constant. And then we know some additional conditions here, don't we? So we know that r is position 0.2 when t equals 0, so that whole thing dies. So c equals 0.2, and then we want 5 sine 2 0.785 over 2 plus 0.2. That'll give us the position, hopefully over here somewhere. So into the calculator we go. 5 sine 2 because it was stored before, over 2 plus 0.2 is 2.7. That seems legit. Seems like it could be there. Let's just make sure I've answered that question. Yeah, what's the distance OB? So 2.7. That is my answer. Okay, 7. Sorry, was that question 7? Yes. Question 8. The line L has... just seeing some of these comments. I was in a maths world of my own there. Yeah, thanks. Got the Lord of the Rings posters up. I've actually got some different different posters that I've been meaning to hang. Yeah, maybe my neighbours can hear me. You know, I've never had a single complaint from my neighbours about maths in antisocial hours. But hopefully not tonight. And hello, Emily. You are here. You are drunk. Seems legit indeed. Okay. So enough of that tomfoolery. Let's carry on with some of the maths here. So find the coordinates where they intercept. So we've got y equals 15 minus 7x there, and we got y there. So 15 minus 7x is equal to x squared minus 6x plus 9. So that means x squared plus x minus 6 is equal to 0. This looks like our good old 2-3 combo. So minus 2 plus 3. So x is equal to 2, x is equal to minus 3. And so, since y is 15 minus 7x, then we know that when x is 2, that implies y is equal to 1. And when x is minus 3, that implies that y is equal to 15 plus 21 is 36. Yeah, so why do we get 2 points of intersection? Well, this is a straight line that looks like that, and this is a parabola that I think is going to look something like, you know, it's going to look something like that. So it's going to go through twice. Okay, it's not going to look exactly like that. But okay, use algebraic integration to find the exact area of the finite region bounded by L and C. Okay, so we actually do need a better sketch here. So minus 336, we've got an interception point, and at 2, 1, we've got an interception point, and the curve goes through 9. Wow, what is this going to look like? So okay, so it's that. So it goes through at 9, and it has a minimum at 3. So it's minimum. So the parabola actually looks something like that. Nice big fat parabola. But curiously, it does have. Okay, this is wrong. So actually, it goes through at 9, it goes through this point up here, it goes through that x equals 2, it goes through a point there, and it actually touches the axis there, because x equals 3 is the repeated root, so x equals 3. Horrible looking parabola, my fullest apologies. And then we've got this 15 here, straight line with a big steep -7 gradient. So when y is 0, we have 15 on 2, which is about 2, so it looks something like that ish. Oh gee, you know what, I'm making such a hash of this. Just can't seem to figure out what I'm looking at here. Let's give ourselves a bit more space, because I've forgotten that L actually goes through those points there, so it actually looks more like that. So it's here. This is what we are being asked to find. Okay, this sketch I think is good enough, even though it's disgusting. Okay, so we want the exact area of the region bounded by L and C. So what we've got is something that looks like that. Here, -3, 2, and then the straight line there, and we're being asked to find that area there. Okay, so this here is 36, this here is what was it, 1. Okay, so we're going to do the area of that trapezium. That's equal to, so we've got a base of a height of 5 there. So 5 times 37 over 2. Yeesh. This does not look nice, does it? Yep. Fine, whatever. And then we want the integral between -3 and 2 of x squared minus 6x plus 9 dx. That's going to tell us this part, and then by doing the area of the trapezium, subtract that, we'll get the area of the shaded bit. So x cubed over 3, take 3x squared plus 9x from 2 minus 3. Oh, even this isn't pretty. So this is 2 cubed over 3 minus 3 lots of 2 squared plus 9 lots of 2. Subtract minus 3 all cubed over 3 minus 3 lots of minus 3 all squared plus 9 lots of minus 3. Okay, so messy. Let's do this in the calculator. 2 to the power of 3 over 3. Subtract 3 lots of 2 squared plus 9 lots of 2. We get 26 thirds. And we're going to subtract all of this nonsense in here. Minus 3 to the power of 3 over 3. Take 3 lots of minus 3 all squared. Plus 9 lots of minus 3 is minus 63. So 26 divided by 3 plus 63 is that. So this whole thing is 215 on 3. And this whole thing is 5 times 37 on 2, which is 185 on 2. So 185 on 2, subtract that 215 on 3, and we get nothing nice. 125 on 3. That'll do. Hope that's right. So, yeah, a bit of a messy question, that one. So, the fourth term of an arithmetic series is 108. And the 11th term is 80. I did a question like this not too long ago. So, fourth term is 108. The 11th term is 80. So how many jumps have we taken? So up to 5, 6, 7, 8, 9. Oh, what am I doing? 9, 10, 11. 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7. So 4 plus 7, lots of the common difference, is minus 28. What am I doing? 7D is, yeah, D is minus 4. Okay, so the first term is going to be, so we need to add 4, add 4, add 4. That gives us 120. That's the first term of this series. Not a series, actually. That should say sequence. I don't know if that's an error or a typo, but it is a sequence. A series is a sum of a sequence. The sum of the first n terms of the series. So this should say the series Sn is the sum of the sequence. So the first n terms of an arithmetic sequence. So we're going down by 4 each time, and we start from 120. So our nth term is that, isn't it? Okay, and then we want to sum from I equals 1 to n of minus 4n plus 124, which is minus 4 times the sum of n from I equals 1 to n plus 124 times the sum of I equals 1 to n of 1. So that is just 124, and this is minus 4n times n plus 1 over 2. So this is minus 2n times n plus 1 plus 124. So that's minus 2n squared, subtract 2n plus 124, and it wants us to take the 2 out, it wants us to take the n out. Now, curiously, this looks like I've made a mistake somewhere, because we don't have that 124 floating around. What do we have? Okay, that is definitely wrong. So, not to panic. This is definitely right, isn't it? We're doing 124 minus 4 lots of n. So when n is 1, oh my hand. When n is 1, we get 120. Unless I've done this wrong. So 108. That's third term, second term, first term, 120. I'm convinced by that. 108. Fifth term, sixth term, seventh term, eighth term, ninth term, 10th term, 11th term, 80. I'm convinced by that. Yeah, I just didn't get anywhere near this. So this is 122n minus 2n squared. check that formula book. Am I doing the sum of an arithmetic sequence correctly? So this says that Sn is equal to half n a plus L. What is L? Okay, it also says it's equal to half n 2a plus n minus 1 lots of d. So let's try it this way. We've got n over 2. Okay, 2 times 124 is 248. I like this even less than the last thing I tried. And then n minus 1 times minus 4. So this is 248 minus 4n plus 4, all divided by 2, all times by n. Okay, so 248 plus 4 divided by 2. Starting to do my head in. 126. Where did that 248 come from? That came from 124. That's wrong. That should be 120 there. So that's 240, 240, 120. I still like this even less. 120 plus 2 minus, there we go, there it is, n, which is 122 n minus 2n squared, and if we pull a 2n out, we get 61 minus n, which is what we wanted. So, thank goodness for that. Thought that was never going to fall out. Now, given that the sum is 1100, so 1100 is equal to 2n 61 minus n. So 1100 is equal to, re-expanding now, 122n minus 2n squared. Let's divide it all by 2. So 61 n minus n squared. So n squared minus 61n plus 550 is equal to 0. Okay, is there a nice factorization of this then? Well, 550 is equal to 50 times 11, so that's promising, because 50 plus 11 is 61. So if we play our cards right, we're going to get n minus 50, n minus 11, and so n equals 50, n equals 11. And the reason we get two answers is because, I'm sure there's a good reason. It's a quadratic, yeah, so the relationship, it's kind of, we start out, we're kind of growing like that, I guess. Or, well, like that really, isn't it? Start out big, positive, and then you're slowly deducting. So I can see why we might get two answers, because we're gonna grow. Yeah, in fact, it's gonna be the other way around, isn't it? It's gonna decrease until we get into the negatives, and then I don't know. Whatever. Fine. So question 9 done. Question 10 of 11. All right, some chunky vectors looking questions now. Okay, this is awkward then. So usually with these kind of questions, you get the diagram. It obviously doesn't want to give us that. So we've got some A, B here. Minus 2 plus, so AC looks kind of like that, I guess. So A, B, C. And we're given AD as well, minus 7 plus 10, so it looks something like that. Okay, and it wants us to find DC. So DC is equal to, well, we'll go to A, and then we'll go from A to C. So dA is 7i minus 10j minus 2i plus 15j. So all in all, it's 5i plus 5j, which is actually equal to that one. I'm sure that's not a coincidence. Hence show that ABCD is a parallelogram. Okay, good. So actually, it's looking something like that, and we're going to show that this is indeed a parallelogram. So we've just shown that DC is in fact equal to AB. So that bodes well. So we've got that this is parallel to this. We now need to show AD and BC are parallel, or equal in fact, because it's a parallelogram. So AD, we've got BC. Let's work that. So BC, we will go from B to A, and then we will go from A to C. So BA minus 5i minus 5j plus 2i, well, minus 2i plus 15j. So all in all, we've got minus 7i plus 10j, which is equal to AD. Look at that. Okay, therefore ABCD is a parallelogram. Nice. Okay, find a unit vector parallel to BD as a simplified expression in terms of I and J. So, BD. Let's go the same way as we did before. We need to go B to A plus A to D. So B to A, minus 5i minus 5j minus 7i plus 10j. So that is, that's an I, isn't it? Not a very well drawn one. Minus 12i plus 5j. Now this looks nice because the root of 12 squared plus 5 squared is 13, isn't it? So root 12 squared plus 5 squared, yep, so one of our Pythagorean triples. So BD, the size, the length, the magnitude is 13. So let's, our unit vector is going to be minus 12 over 13i plus 5 over 13j. Okay, this question will not end. The point E lies on BD such that BE to ED is 3 to 10. Jeez. Right, what was BD? BD was minus 12i plus 5j. So BD is minus 12i plus 5j. So we've got some vector, B to D. And point E is such that for every 3 bits here, we've got 10 bits there. Find AE as a simplified expression in terms of I and J. So, well, BE is going to be equal to 3/13 of BD. Whew. Now AE is AB plus BE. So AB is 5i plus 5j plus 3 on 13 of BD minus 12i plus 5j. And you know what? I'm getting bored of this question, so let's just do it in the calculator. So it's going to be 3 on 13 times minus 12. This is a calculator paper, so it's perfectly fine. So that's 29 on 13 I, and then 5 there, plus 80 on 13 J. Okay. Not one of these questions. Come on. Not now. Point F is such that DCF and AEF are both straight lines. Right. Of course it is. So A, B, C, D. We know that to be a parallelogram. So something like that. We've got BD, and then we have this point E here. And now it's telling us that point F is such that DCF, so F floats out here somewhere, and AEF are both straight lines. So F, AEF, DCF. They're both straight lines. Find the ratio DC to CF. So it's basically asking us how big that is. You know. So now the way that I always do these questions is AF is some scalar multiple of AE. And we know what AE is. We worked it out here. So that's fine. And we also know that DF is some other scalar multiple of DC. And we know what DC is, don't we? DC we worked out to be equal to AB. So let's make a note of that. DC is, I'm going to do this in column form now because, you know, it's I and J nonsense. So we have what? What's the point in that? Well, that's good because now AF is AD plus DF. So AD was minus 710 plus DF, which we are saying is mu lots of 5, 5. And we are saying that this is lambda of this horrendous 29 on 13, 80 on 13. And these must be the same. So minus 7 plus 5 mu is equal to 29 on 13. And 10 plus 5 mu is equal to 80 on 13. Okay, bit of the old simultaneous equations. So if we subtract these, we get this. Oh, where's my lambda gone? Oh, sorry, of lambda. So we subtract, let's call this 1, let's call this 2, let's do 1 subtract 2. The mu's die, so 10 subtract minus 7 is 17. 80 subtract 29. Please tell me that's a multiple of 13. Oh, come on! But 51 is a multiple of 17. So that might help. So that's 51 on 13 lambda. So 17 times 13 is 221 divided by 51 gives us lambda is 13 thirds. Okay, then. So that means that mu is going to be equal to. So if we times that by 29 on 13, and then add 7, and then divide by 5, I get mu is 10 thirds. And you know what? of all the answers we could have got, that is not terrible. Because what this is telling us now, so df is equal to 10/3 of that. So if this is x, then this is 10/3 of x. Yeah. So as for the ratio dc to cf, that means that this is for every 3 units here, we've got 10 units there. Yeah. So it's 3 to 10. That's the answer. Or is it 10 to 3? DC to CF. That is, well, 1 to 10/3. I always screwed this up. DC. I've got to be careful. Yeah, we just got to be careful because what are we saying? We're saying that we've got some length DC, and that this length here is 10/3 of DC. That's what we're saying. So what is the ratio of DC? The ratio of that to that. That's what we want, because this is CF, this is D, this is F, this is C. God, my brain, it's just gone. It just will not compute the answer to this. This is amazing. Just give me a minute. Give me a minute. You get to this point where no matter how hard you stare at something, it just doesn't make any sense to you anymore. So, if this is 1 unit long, this here must be 7/3 units long. So the ratio is actually going to be 3 to 7, isn't it? Of course it is. Okay, so with that out of the way, we're almost done with this paper here. Just one more question. Ooh, okay. Hand is really killing me. I did not have this problem last year. So. Figure 3 shows the right pyramid A, B, C, D, E. Oh, this looks so faffy. The base of the pyramid A, B, C, D is a rectangle. C equals to 16x. The diagonals of the base intersect the point X. The edges EA are all, yeah, blah, blah, blah. Okay, the size of the angle between EA and ABC. Okay, so we've got 45 degrees there. Find, in terms of X, the height of the pyramid. Okay, so AC is equal to square root of 12x squared plus, 16 squared x squared. So I wonder if that turns out to be something nice. Yep, so that's 20x So that there is 20x. So we've now got a triangle, base 10x. Oh yeah, well, it's 45 degrees. It's an isosceles triangle, so that must be also 10x. The length of EA. So this is going to be the square root of 100x plus 100x squared. So that's root 200x. I'll leave it like that. Find in degrees to the nearest 0.1 the size of the acute angle AEB. So AEB. Yeesh. So it is that angle there. Oh, sorry, between the planes AEB and ABCD. So actually, what we want is something that looks like that. So this triangle here, we want that angle. Let's call it theta. So we're looking at a triangle that's like that there is 6x. We worked out the height to be 10x, didn't we? So theta. Okay, so that means we've got a nice tan theta is equal to opposite over adjacent. So arctan. Okay, and we're back in the world of degrees. I swear they intentionally alternate these questions so that you intentionally make a mistake. So theta is equal to 59 degrees. Okay, it's done that one. The acute angle between the planes BED and AEC. So BED. So that's that kind of triangle that's embedded in there. And AEC. What? Right. It wants that angle basically, doesn't it? Because it's the, if you imagine them kind of, yeah. So, what are we looking at here? Very fiddly question. So we've got a triangle. Let's make it this a right angle triangle here. So this triangle here is 10x. (6x), and we want that. Let's call it phi, and we actually want 2 phi. So let's not forget. In the end, we want to do cos phi is equal to 6/10. So phi is equal to arc cos of 6 divided by 10, and then times it by 2. Ooh, we got 106. So that doesn't make sense. We've got a big thing here. If this is bigger, then your acute angle is going to be that one. So we'll do 180 minus that, and we get 73.7 degrees, skipping a few steps there. And we've done that one. The area, come on, end this question already. AED, the area of that is 250 centimeters squared. Ooh, honestly. So, AE, we worked that out to be root 200x. So let's just get all this information down into one nice triangle here. So it is isosceles. We've got a 12x, and we worked out so this is A, E, D. We did work out that this here is root 200x. Okay, and then we know the area is 250. Okay, so it is isosceles, which makes it a bit easier. So we will Pythagoras our way to, that's called that y. So this is 6x. So y squared plus 36x squared is equal to 200x squared. So 200 minus 36, well, just type it in totally the wrong numbers here. 200, take away that, and then rooted, so root 164 x. Now we're going to go for the classic half base times height. So half 12x times root 164 x is equal to 250. Okay, so in other words, 12 root 164 x is equal to 500. So x is equal to 500 over 2 root 164. 19.52 to 4 significant figures. Oh boy, that was actually surprisingly tough. I actually think I struggled with that quite a bit more than some of the A-level questions. So for a bridge between GCSE and further maths, you know, they're not messing about. Suppose all the stuff in there. I mean, this question here, this is GCSE level content. You don't need any A-level content to do this. It's just more fiddly, and that makes it more challenging. Okay, so that's that one done. So, depressingly, I'm only halfway through the number of papers that I've got to do, which is just insane. Can't believe how much time I've lost. I've got to do 12 papers in the next 9 hours. Right. But I do need something to eat, so I will be back. Right. Okay. So very nervous actually now about the time I've got left to do this. Can't believe I've done so little. So yeah, still 13 papers there. It's insane. I can't believe I've done like nothing. Well, not nothing, but I've spent so long doing it. So this is the point where I need to kind of hunker down, stop talking, give my throat a rest, eat some food, and just put some music on and try and focus and try and power through quite a few of these. I've got an average of like 45 minutes per paper now, so and that is not good because there's some tough papers in there. They're not all GCSE easy rubbish. You know, there's some difficult stuff here. So I am going to just adjust that paper counter to paper 30. I'm going to carry on with the IGCSE papers. So paper 13 now. Okay, I'll just mute that audio there. So let's go. Let's put a bit of music on. And okay, let's just try and get through as many of these as I can. Can't even remember what's on the IGCSE. Wow, hefty formula sheet. Okay. Is there a calculator on this? Yes. Okay, so that was a bit of an improvement. I did 2 papers in an hour there. It is 4 o'clock in the morning here. I've been doing this for 16 hours. 8 hours to go. So at this stage we are 2/3 of the way through. So we're actually going to end the stream on this part here, and we are going to go over to part 3. So if you are still watching, click the link down below to go over to part 3, and I will see you there.